Phil, Nayesh, welcome to the show.
Thanks. Great to be on.
Pleasure to be here.
What exactly is the Big Bang, Phil?
Well, people think they know, but actually there's quite a bit of controversy as to what we even mean by the term Big Bang. So we talk about two definitions, the hot Big Bang, and that's just the idea that the universe evolved from a very hot, dense state. And then after that, it's expanded and expanded and it cooled, and then galaxies formed, and then planets formed, and us. But there's another definition of the Big Bang, which you might call the Big Bang singularity.
Mm-hmm.
That says that 14 billion years ago, time stopped ticking. This was the beginning of the universe. So that's based off of theorems proven by Penrose and Hawking. And what's interesting is that neither Penrose nor Hawking actually stood by those theorems.
Mm-hmm.
They actually think that some of the assumptions in the theorem don't hold in reality. And so maybe we shouldn't trust the idea that the Big Bang was the beginning. And in fact, Nayesh and I went to a large conference in Copenhagen, and we surveyed physicists. We asked them all sorts of controversies within the field. And in fact, the only one where we got a majority view was that the Big Bang should not be considered the beginning of time. Rather, it's a much more modest claim that the universe evolved from a hot, dense state and then expanded afterwards.
Interesting. And that hot, dense state that you're referring to is not the same thing as this singularity, right? When people imagine the Big Bang, almost by definition, it's the bang at the beginning. It's where everything got started. And so when you describe this hot, dense state, people might be imagining taking all of the matter and shoving it down to the size of an atom. But this hot, dense state is not that singularity that people imagine. This is sort of a little bit later on in the history of the universe. If there is such a thing as a singularity or whatever, this hot, dense state is slightly bigger.
The singularity is what would happen if you traced it back using certain assumptions.
Mm-hmm.
So we know that it was hotter and denser in the past, hotter and hotter, denser and denser as we trace it back. And if you take certain assumptions, as Penrose and Hawking did, then you get to this singular state where the density, in some versions, you might say the density goes to infinity. But the point is that the clock stopped ticking.
Yeah.
And that's the beginning of time. But we don't have to assume that. And in fact, lots of cosmologists doubt that. They don't think the Big Bang was necessarily the beginning. But no one doubts that there was some kind of Big Bang. And the hot, dense state is what everyone agrees on. But what came before that is the open question.
Interesting. The book, by the way, ladies and gentlemen, is Battle of the Big Bang. And the first question, of course, is going to be, what is it exactly that we're battling over? I think it's a great title for the book. We spoke about this when this book was in its sort of formation, and one of the working titles was "What Banged," and this is a better title. Like this is going to sell more books.
Well done for the marketing team.
I think that's definitely the pro. Mm-hmm. But the reason I liked the title "What Banged" was because one of the great sort of questions for people who are scientifically minded, people who are religious, they'll say, oh yeah, sure, we've got this Big Bang stuff going on. But what we were really interested in is what made it bang, like what actually happened at the beginning. So it seems like when we're talking about the Big Bang, there's this question of this accepted theory of something near the beginning of the universe, maybe, that everyone agrees on, the Big Bang. But there's still this great mystery, what exactly was the Big Bang and what banged it and all of this kind of stuff. Nayesh, what is it about the Big Bang that we can know that isn't part of this mysterious, we don't know this, we don't know which model? What is it about the Big Bang that is this sort of uncontroversially accepted element of, early universe cosmology? And why can we be so confident about this hot, dense version of the Big Bang?
That's an excellent question. And before that, I was just looking at your hands, and it says this Big Bang, and you said there is one of the common myths about the Big Bang is that it was a point where things started, and Big Bang is in fact something that happened everywhere. So when you say Big Bang, you shouldn't do this. You do it like this. It's everywhere is Big Bang.
Ooh, so how do you move your hands to do the Big Bang?
Everywhere. I don't know. I've never thought too hard about this. This is the Big Bang. I guess it's the Big Bang dance. Yeah, Big Bang. Yeah. So it's everywhere, and there is a bang. But let's get back to your question.
Yeah.
So what do we know about the Big Bang, and what don't we know about the Big Bang? So talking about the Big Bang is kind of like talking about the sun, right? That's kind of uncontroversial. The sun is hot, right? We feel the heat from the sun. It must be hot, and then we can use a telescope. Of course, hopefully you shouldn't use a regular telescope. You need to put the right filter, otherwise you're going to lose your eyes. But you can look at the sun and you could see it shines. There's a lot of light coming out of it. So based on the properties of the light, you can say that it's a hot surface. But what's inside the sun is a much harder question. And for that, you have to rely on models and a lot of other things. Vibration of the sun, try to figure out what's going on inside of the sun. Big Bang is basically the same thing. We have very good evidence, incontrovertible evidence that there was something very hot that happened there. We're looking back. Now, the light we see is not quite the same as the light of the sun. It's colder. It's in microwave. In fact, it was, most people think it was discovered, this evidence for the Big Bang, the cosmic microwave background, in 1965 by people in Bell Labs, Penzias and Wilson. We point out that a little known fact, it was a Canadian, where I come from, who discovered this cosmic microwave background 25 years earlier. In the 40s. And so basically the same way that we see this heat from the sun, or we experience or see the light from the sun, there is a heat from the Big Bang that we get to feel. It's colder because Big Bang happened a long time ago and the universe has expanded since, so it's kind of cooled down that temperature. But nonetheless, we have detected it in various ways now. So there was this hot phase, and that's the thing that we know, and we can kind of go and probe the evidence of this hot phase the same way that we can look at the surface of the sun and look at the spectrum and say that there are these things that must have been in the sun. We can study the universe and learn about things that could have come out of that hot phase. But then what came before that hot phase? Was it a hotter phase? Maybe it was a colder phase. Those are parts that become kind of more speculative, because we're starting to kind of run out of good theories that could tell us what might be happening. I mean, again, there's analogy with the sun. We've known the sun for millennia, since humans have been around. But what's inside the sun, it's actually pretty recent that we know what's going on, because for centuries we didn't know why the sun shines, and it wasn't until early 20th century that we discovered nuclear physics. I mean, all the other sorts of energy are just not efficient enough. The sun would run out of energy within like a few thousand years or a few million years. It wasn't until we discovered nuclear energy that we realized basically all stars, including our sun, are nuclear reactors. And that was the missing bit of physics that kind of had bewildered physicists or astronomers for centuries. And when we found that missing bit of physics, then we could actually model the stars and the sun in particular. That for the Big Bang, we still have that missing piece of physics. And this is kind of the theme across our book, that the problem is gravity and quantum mechanics both become very strong as we approach the Big Bang. And we don't really have a unifying theory of quantum gravity. There are many proposals for this. But since we don't really have that theory, we cannot really come up with a good unified story the same way that we have for the sun. So the same way that we are waiting basic nuclear physics eventually solve the mystery of what happened to the core of the sun. That hasn't happened for the Big Bang yet, but that's where we're going, and that's what we're trying to do.
So we've got some good evidence for this hot, dense, early state of the universe. Right. And you've just mentioned this cosmic microwave background radiation, which many listeners might have heard of. And there's that wonderful story of Penzias and Wilson, who are sort of, I can't remember what it was they were actually doing when they kept getting this hissing. They were working at it was like a telecommunications.
Yeah, they were working for Bell Labs.
Yeah.
So yeah, they were a telecommunications company. In fact, there's an incredible irony here, because one idea for what might have come before the Big Bang is something called the Big Bounce. So there was a contracting universe and an expanding universe. And in fact, that what was happening at Bell Labs early on, in the early 60s, was they were testing communication satellites. And there was a documentary made about what they were doing. And the name of the documentary was called The Big Bounce, because they were bouncing signals off satellites.
That's so fun. I love the way that these like myths and stories crop up in the history of cosmology. Not all of which are true, by the way. Like I have been telling people on this podcast for years that the term Big Bang was made up by Fred Hoyle to make fun of people who believed in this ridiculous but there's this idea that Fred Hoyle, who's one of the sort of opponents of this beginning of the universe view, is on a radio station and he goes, these guys believing in their Big Bang, and that's where the word comes from. Fred Hoyle did come up with the term, but it wasn't pejorative, right? If I
No, there's no evidence that it was pejorative. People assume it was pejorative, maybe because he was an opponent of the Big Bang. But what they forget is that he was also one of the main popularizers of science at the time, and he was trying to explain the rival theories to his audience in a way that could give some sort of metaphor, because he was on the radio, there's no visual aids. And in fact, Gamow, who was one of the proponents of the Big Bang, told his students that that Hoyle had used it pejoratively in a debate that they did on the BBC radio. But a historian of cosmology, Helga Krog, showed that there never was such a debate. He'd made it up. It just didn't happen. So that's where the myth of the pejorative term comes from, but there's just no evidence.
It's a shame. It's such a good story as well, though, isn't it? It's always fun when people take on these labels. Another myth. Mm-hmm. Well, I say a myth. Another myth that you sort of hinted at just then, Niayesh, is the idea that Penzias and Wilson sort of geniusly discover this sought-after microwave background radiation. This is like, they call it the afterglow of the Big Bang.
Right.
The Big Bang happens and it leaves this pattern of heat all across the universe, which if the Big Bang occurred, we should still be able to detect today.
Yeah, that's right.
And so there were sort of people looking for it, and then Penzias and Wilson, geniuses as they are, discover it finally, prove the Big Bang, and win the Nobel Prize. It is true that they got the Nobel Prize, but they discovered it by accident.
That's right.
And just up the road from people who were working on trying to find it, and were nearly there. Even though they found it by accident, they're the ones who got the Nobel Prize. And it had been detected earlier, just not recognized.
That's
well.
right.
So it's this incredible story of how all the evidence was sort of there, but it just took the right people to put it together. There's so much historical contingency involved in actually finding the right evidence in the right context.
And it's amazing how these kind of discoveries happen, because like often there are like so many pieces of evidence that are here and there and pop up. And in the hindsight, you go back and say, oh, we inferred this from this and from that. But anytime, and I mean, it happens over and over in the history of science, that when you're leading up to like a big discovery, there are all these bits and pieces that are there, but just people don't see it, and it just maybe takes a bit of luck. And in this case, Penzias and Wilson called up Bob Dickey at Princeton, who was a professor and has been looking for this basically for years. And he said, okay, we see this hissing thing. And then basically he said, oh, yeah, this is what we were looking for. That wasn't their intention. But it's amazing. And it tells, I think it's kind of, there's a broader lesson here, which is about the role of serendipity in discovery. So Bell Labs, for example, is a commercial company, right? They were trying to make communication and phones. But this Bell Labs was actually amazing. They did a lot of research, very fundamental research. And nowadays, it doesn't happen very often. Like companies want to make money and they don't really focus on fundamental science or just research and development as much. And it's all kind of reversed to the government, and we know what happens with the governments. Governments kind of their budget cuts and stuff. But so the question is, you do need this investment in serendipitous science, because you never know where these things are going to come from. And these connections are random, but if there are enough of these triggers, eventually they're going to connect. And I mean, that's what happened for the CMB, that people were anticipating something, and then there was enough investment in direction of kind of advancing technology to find it. And then it eventually happened. And I mean, I'm amazed at what's going to be in the next discovery. It might be already in the making. There might be pieces and bits that are here and there. People are seeing things they cannot quite connect the dots. But if there are enough of them, hopefully those connections will happen again. Mm-hmm.
But of course, the first evidence for the Big Bang, we've had for thousands and thousands of years since the writing of Genesis, of course, which predicted that the universe began to exist out of nothing, that God said, let there be light, ladies and gentlemen. Mm-hmm. And now we have this evidence that exactly that has occurred. In fact, it was a Catholic priest who is credited with sort of first maybe coming up with this idea of the Big Bang. I never like to pronounce his name, but it's something like Georges Lemaitre.
It's Lemaitre.
Lemaitre,
yeah.
with a bit of a phlegm in there somewhere. And he's a Catholic priest. And when he sort of theorizes this Big Bang, and when the evidence starts coming in, Pope Pius, the Pope of the Catholic Church, declares publicly that this is the evidence of the fiat lux, of the let there be light. So quite clearly, at the very least, we've got evidence pointing towards, even if it's just this sort of, at that time, just the cosmic background radiation later on and the universe's expansion and stuff, we're looking at evidence for the beginning of the universe, right?
Well, it's interesting you talk about Lemaitre because he was a very jovial chap, apparently, always in a good mood, except for that moment when when the Pope declared the Fiat Lux and said we're going to use the Big Bang to prove Genesis. Lemaitre was very, very unhappy about that. He wanted to keep his science and his religion absolutely separate. And he had a meeting with the Pope. Now, no one knows what was said at this meeting, but the rumor is that he told the Pope, do not use the Big Bang as evidence of Genesis. This is a very bad idea. And in subsequent talks, Pope Pius never mentioned the Big Bang again. So I think it is good advice from Lemaitre not to use it. And actually, I was brought up Hebrew, so I actually know the Hebrew. And I don't think it's even been translated properly. I don't think it says in the beginning, God created the heavens and the earth. What I think it says is, and a lot of Hebrew scholars agree with me, is that when God began to create the land and the sky, and we know it's land and sky because the words in Hebrew, haaretz, means the land. I mean, lots of Jewish children will sing songs about the land of Israel, haaretz Israel. And the hashemayim is the sky. It's where the birds fly. So I don't think Genesis is in any way talking about the beginning of the universe as we know it. In fact, a lot of rabbis thought there was something before the creation. There was a chaotic state. And so when God moves over the face of the waters, this is a representation of the primordial chaos. And it's very, very similar to the Babylonian myth, the Enuma Elish. And lots of people have drawn parallels to the Enuma Elish. So much more likely what's going on in Genesis is a sort of monotheistic repackaging of this ancient Babylonian myth. And indeed, in the Babylonian myth, there are sort of 7 tablets of creation. The gods rest at the end. They defeat the sea monster called Tiamat. And the face of the deep, the word deep in Hebrew, is something very, very similar to Tiamat. So I don't think there's any real description of the Big Bang in Genesis. And it doesn't really say that the universe had a beginning. It doesn't talk about a beginning of time. It doesn't say the universe came from nothing. And ironically, neither does the Big Bang say the universe came from nothing. It just says it came from a hot, dense state. So not only does the Big Bang not describe the universe from nothing, but neither does Genesis.
It's a great irony, isn't it? I mean, I did an episode a while back on the translation of this particular passage in Genesis. In the beginning, God creates the heavens and the earth, or when God created the heavens and the earth, or the land and the sky, he did this. And it's the difference between there sort of being this empty frame at the beginning of the cartoon. I had this guy called Magnify on my channel, and he sort of imagined it like a cartoon strip. In one interpretation, the first sort of square is like an empty box. That's the beginning. And then God creates. Whereas on this other interpretation, in that very first cartoon box, you've got God, you've got the primordial matter, and God sort of fashions it. And this is a great irony, isn't it? Because, people think that Genesis says that there's a beginning of the universe and the Big Bang proved it, but actually, translation-wise, maybe it doesn't. And actually, if we're careful enough, maybe the Big Bang doesn't either. So when people hear the Big Bang, they're going to think we're talking about the beginning of the universe. That's what the Big Bang is by definition, right? We just talked about these two different definitions. Yeah, why is the Big Bang maybe not the beginning of the universe? I thought that's kind of what the whole thing was about.
Right. So, of course, that, like many questions, that depends on what you mean by the beginning. So the Big Bang, in some sense, is the beginning of something. It is the beginning of where we start to understand how to describe universe, to talk about universe in the language that we can speak right now. So we have this hot, dense state, and then we can go back. And then at some point, kind of things become less and less clear, basically more and more fuzzy. So, the earliest we can use the laws of physics, and we have direct ways of kind of testing what we say about the Big Bang is maybe a minute or so after the so-called initial singularity. That's where the elements were formed, in particular hydrogen, helium, some lithium, deuterium. So these were forged at the Big Bang. Of course, they're forged in the stars as well, but primarily at the Big Bang. And going before that, we have ideas, but then we kind of going on a limb. We kind of take our ideas and try to push them, extrapolate them to their logical conclusion. And that leads us to a point where if you push them, so it's kind of you're saying that this car is moving that way. Okay, so it's going to keep moving this way at, I don't know, 60 kilometers an hour. And maybe it's going to go that way for an hour. Maybe it's going to stop in 1 minute and take a turn. You don't really know because you just know what it's doing now. And that's based on what we're saying. We could kind of extrapolate, but it's like extrapolation could be wrong because it could take a turn. And we're using the rules that we know to do this extrapolation, but the rules that we know kind of stop at some point.
This is like a backwards extrapolation.
Yeah, exactly. Backwards.
Like sort of shrinking the universe down and down.
That's right.
Just assuming that keeps going.
Assuming that it keeps going, right. Assuming that it keeps going, it takes us to this point where kind of time stops ticking, and densities and pressures and temperatures could blow up, basically go to infinity. So that is what Penrose and Hawking back in the 60s called singularities, and they thought it was unavoidable according to those theorems. But those are based on assumptions, and we know that the assumptions fail, and almost every practicing physicist thinks at least one of the assumptions that lead to singularities fail at some point.
So they think that there's this thing called the singularity, which is also what's at the center of a black hole, famously.
That's right.
It's Penrose's work on singularities in a black hole that Hawking sort of cottons onto and says, hold on a second, if you take that singularity business and play it in reverse, you might get something like the Big Bang
a
singularity at the beginning of the universe. And this is a sort of reversing of time and an extrapolation, or whatever the opposite of an extrapolation is, towards the Big Bang. You just said that though relies on a few assumptions. What are some of the assumptions that this extrapolation relies on?
Excellent. So there are basically four assumptions that go in these singularity theorems, and we kind of go over them in our book in a lot of detail. The first one is gravity is always attractive, right? Which we think should be true. I mean, gravity, kind of its name, it says attractive. Except that we now have incontrovertible evidence that gravity is not attractive on larger scales. We have this thing called dark energy, or cosmological constant. We've known that for basically almost 25 years now, that expansion of the universe is speeding up. So right now, this very minute we're talking, on very large scales, gravity is not attractive, it's repulsive. So, of course, back in the 60s, they didn't know that. So they assumed gravity was attractive. That's assumption number one. Assumption number two is we have 3 dimensions of a space and 1 dimension of time.
Right.
That's, of course, I mean, everybody agrees there's 3 dimensions of space. X, Y, Z can go up and down, left and right, front and back. And then there's time is ticking. But it doesn't have to be the case. And in fact, as we go in detail, many theories of gravity suggest that there might be extra dimensions, either the extra dimensions of space or time. So that's another possibility. Or maybe you could get rid of one space and add one time, or vice versa. Maybe you can no time and 4 spaces, etc. So assumption number 3 is that there are no time loops. Basically, time machines don't exist. And I mean, this is, of course, subject of basically infinite fascination, science fictions. Could there be time machines? Could there be not? And I mean, another chapter in our book that we go into is, there could be very plausible scientific scenarios where there are time machines now. Not all favorite science fiction movies may come true, but there could be some versions of time machines that exist. And assumption number 4 is at some level at the heart of basically any theorem, is that you need to assume some mathematics, basically. And the mathematics was mathematics of Einstein's theory of general relativity. But that also we know it has to break at some point, because quantum mechanics is this other theory, as I mentioned before, that we have, which is very successful. The reason you and I can talk, your viewers can actually watch us, is because engineers have used the rules of quantum mechanics to engineer basically technology for us to be able to communicate. So rules of quantum mechanics are very, very successful, happen to be inconsistent with mathematics of general relativity. So that needs to be revised as well. So these 4 assumptions, probably at least one of them, maybe all of them, fail at some point. So this idea of kind of extrapolating back in time, that definitely fails. And that opens up kind of the door for all imaginative ideas that we still have to put in within straitjackets. So this Feynman has this famous quote that science is imagination in straitjackets. So we are free to imagine things because there is no definite answer at that point. But still, what comes out of whatever we imagine should match our detailed observations of the Big Bang. Cosmic microwave background, distribution of galaxies, the geometry of the Big Bang, the sound waves that we measure coming out of the Big Bang. So these are all the things that whatever imaginative, creative thing you come up with has to explain.
Mm. And this is no joke, ladies and gentlemen. I mean, all of this talk about time loops and the Big Bang not being the beginning of everything. One thing that I love about this book is I don't know what you consider the genre of this book to be, whether you consider it to be, it's kind of a history in part. It's like an overview, almost like a survey. But what this book does, Battle of the Big Bang, should become clear to people now that the battle is for the model of what banged, you know? And the great thing about the book is that you sort of remain agnostic. I mean, not personally agnostic, but the book is just exploring these ideas. And so if you're interested in this stuff, the book just sort of just goes over these ideas and says, look, here's an idea, you know, take it or leave it. And that's why I love this so much, because it's one of those books that it doesn't profess to have an answer. So you just have to sort of go away and give it some thought. And one of the big questions is that throughout all of these different models, and you talk about some, 25 or so different models of what the Big Bang actually was and how it worked, is you've actually got like a cheat sheet at the end, a big table of like, does it involve inflation? Does it? Yeah. And one of the columns in this table is, does this model say the universe has a beginning? And the majority of them say no.
That's right.
So hold on, like, if the Big Bang is not the beginning of the universe, and if you've got this whole table which says here are like dozens of models of the Big Bang that don't say that the Big Bang is the beginning of the universe, then what is the Big Bang and what on earth came before it? I thought that talking about before the Big Bang didn't make any sense. It's like asking what's north of the North Pole.
That's right.
So what are we talking about?
Yeah, well, we're talking about not the beginning of the universe, but rather the end of our current theories, and what we need are better theories. So it might be that Einstein's theory of general relativity tells us the Big Bang was the beginning, but almost nobody in physics thinks that Einstein's theory of general relativity is applicable at the Big Bang. As Niayesh said, we need a theory of quantum gravity.
Is that because the Big Bang is so small? Or like, why is it that general relativity breaks down at the Big Bang?
So I wouldn't necessarily say the universe is small at the Big Bang. It could have been infinite at the Big Bang. It could be infinite now. We don't know how big the universe is. Rather, it was denser. That's the point. It was much denser and hotter in the past.
But what's smaller?
So what's smaller is, if you like, what we would see. So our horizon, that's shrinking. So the observable universe, you might say, is getting smaller.
But what does it mean to say that it might not have actually been small? I mean, again, like, it's difficult to imagine, right? But when I think of even just the Big Bang of the hot, dense state, forget the singularity, I'm imagining in my head, again, here go my hands, something sort of shrinking. Is that like the wrong way to be thinking about it?
So think of like this room. Yeah. That's what you can see at the moment. I can't see what's outside this room.
Yeah.
So similarly, we can see out quite far, but nobody thinks the distances that we can see, billions of light years, is the whole universe. So that bit that we can see, you can think of that as shrinking.
So the observable universe was smaller at some point.
So I have another analogy for you, actually, which I think it's even mathematically reasonable, actually. So we know about black holes. You heard about black holes. Like, black holes have these horizons, right?
Yes.
That if you fall into them, you cannot get out. Like event horizon of a black hole.
The point at which not even light can escape.
Not even light can escape, right? So if you're outside, in principle, you can shine a light, but if you fall inside of it, even if shine a flashlight, it cannot get out, right? Universe is actually, even today, the universe is like a black hole inside out. Right? So we have a horizon, but instead of we being outside the horizon, we're inside the horizon. So we are surrounded by it, and there's a point, basically, if you go beyond that, you cannot return. So we cannot see people beyond that horizon. And it's kind of like they're falling to the black hole, except that we are in the center, and the horizon surrounds us is everywhere.
Whoa. Okay.
Yeah.
And is that to do with the expansion of the universe?
It has to do exactly. So the expansion of a universe is actually stretching everyone, is pulling everyone apart, and at some point there is a point that they are being pulled apart in some sense faster than the speed of light, which you think like fast it should be impossible, but this is the thing. I cannot move faster than the speed of light relative to you, but the universe somehow can move faster than the speed of light. It's something that's in fact within the mathematics of general relativity itself. You're not really violating anything because there's no particle that's moving faster than the speed of light. It's the space itself that's moving faster. But then basically what it's doing is that so those things are just kind of moving so fast that we cannot see them, and they're outside. So this, you can think of it as expansion of a space, or you could think of it as just like the way you think of a black hole, but inside out. And the distance to this horizon just gets smaller and smaller as you get closer and closer to the Big Bang. So a universe, so the space could be infinitely big. We don't know, but I mean, it's consistent with observation that the space is infinitely big. But the amount of a space that we can see up to the horizon, basically, the cosmological horizon, becomes smaller and smaller as you get to the Big Bang.
Yeah, as if we had like a huge sort of fabric, and I just took this little bit of the fabric and stretched out that bit of fabric.
That's right.
And that like within that bit of stretched fabric, you could see everything around you like flying apart and think that all must have come together, but it could just be one tiny little ripple in a massive, massive fabric.
That's right.
I love this black hole inside out thing. That's really good to think about. And I think for people to understand, if the universe is expanding, it means, like, if something is expanding away from you, it means that the further something is away from you, the faster it's moving away relative to you, right?
That's
you can sort of imagine stood in the middle of a fabric, or the famous example of a cake, like a raisin cake or a chocolate chip cake. I know how much you hate raisins, Phil. Expanding. And like if you were in the middle of that cake, the raisins or the chocolate chips just next to you would be moving away slowly, and the ones at the very edges would be moving faster. As the universe gets bigger and bigger, at the very edges, those chocolate chips are moving away so fast that if they're moving faster than the speed of light, or rather the space is moving, so that it has that effect. If that chocolate chip is moving away from you faster than the speed of light, then when light comes off that chocolate chip, it can't reach you.
That's
because
right.
the whole thing is moving away faster than the speed of light.
Absolutely.
It's kind of like, a car driving away faster than the speed of sound. If you play a sound, that sound's never going to reach you because it's zooming off with the car. So you just reach the limit of our observation. Right? Like anything that's beyond that point, even if it's emitting the brightest light on Earth, it just doesn't have the time to reach us because it's all expanding away from us. And so
I think I should stop you there. Please. I mean, as a student of relativity, I say you shouldn't compare sound and light in that extent, because in fact sound always travels with its medium, right?
Oh, sure.
So so no matter how fast the car moves, the sound that comes to us basically is the speed of sound with respect to air, which is
whereas light just
light is independent of frame, right? So I mean, I think it would be true that if there's a sound and they're moving, like you have a supersonic plane, then you may not hear, basically, because it's moving very fast in the speed of sound. But if the supersonic plane make a sound, we're gonna hear it, because the sound is propagating with respect to.
Anyway, I think it's helpful to visualize. I mean, I guess if people are struggling to imagine this, imagine like a car moving at 10 kilometers per hour to the right. And imagine that it emits, relative to the car, it emits like a particle that travels at 5 kilometers per hour in the opposite direction.
That's right.
Like, because the car is moving 10 kilometers that way and it's moving relative to the car, that particle will actually like be moving away from you, I guess.
That's right.
And so it would never actually reach you, even though it's been emitted from the car towards you. Because the overall movement is away, that particle goes away. And so light would function in a similar way, that the light would, relative to you, be traveling away and would never reach you. And so we just reached like the limits of our observation. Right? And so, okay, maybe then the Big Bang is like a localized ripple in a larger fabric, but like, how can we begin exploring that question? If we're talking about, anything outside of the Big Bang being like, by definition, beyond our observational capacities, how can we even begin writing a book like The Battle of the Big Bang? Surely the only answer is we have absolutely no idea and can never have any idea.
Good. you were asking what is this book actually. I just had an idea. You heard about the Schrodinger's cat. There's like a dead cat and alive cat. It could be the same. So this book is like a Schrodinger's book in the sense that it's a fiction book and a non-fiction book at the same time. So we're trying to get to what's fiction, what myth about the Big Bang. And there's a lot of myths about the Big Bang. There's some that we talked about, but there's also myths that kind of cosmologists believe in, and they think is supported by evidence, or they think is proven. For example, there is a leading theory of the Big Bang known as inflation, which suggests that the universe was expanding very, very fast, at a very, very tiny fraction of a second, was doubling basically every tiny fraction of a second, expanded by 30 orders of magnitude or so.
This is right near the beginning.
Right near the beginning. And this is... so this is an idea. Now, I'm going to tell...
As you explain that, what's the difference between... the Big Bang theory as a whole is a big expansion at the beginning of the universe.
Yeah.
So what's inflation as distinct from just the Big Bang expansion?
Very good. So the difference is whether gravity is attractive or repulsive, right? So the expansion is expansion, but you remember I told you that right now the expansion is actually speeding up.
Yeah.
That it is expanding, but then it's actually getting faster and faster. So the gravity is even speeding up.
Mm-hmm.
So inflation suggests that something like that happened near the Big Bang, or in fact, just before the Big Bang, before the hot Big Bang. Yeah.
Depending on the terminology, right?
Depending on the terminology,
because
exactly.
Just to be clear, when you say before the Big Bang, if by the Big Bang we just mean the hot, dense state,
exactly,
then there could easily be something before. When you say before the Big Bang, people need to get rid of this idea that you're talking about before the singularity or before the point of creation. The Big Bang can just be used to describe this hot, dense state.
That's right.
Inflation is the idea that there is this like exponential speeding up kind of growth rather than just a sort of linear growth.
Yeah, exactly. So this repulsive gravity, the idea is that there was repulsive gravity much, much stronger than it is today, back then, before there was this hot, dense state of the Big Bang. And that kind of stretched the universe by 30 orders of magnitude. Basically, there are 100 doublings or so, basically. The universe doubled in size in a tiny, tiny fraction of a second. Many, many times. And because the reason it could do it was gravity was repulsive and very, very repulsive. And what it does is that it kind of takes a tiny speck where you could have like tiny quantum fluctuations in it, and it stretches it across the universe. So you get this very big universe, which is very uniform, the way we see it, with tiny fluctuations, which turn out to basically become these sound waves that we see that basically form, we see the ripples in the cosmic microwave background, and then eventually they form galaxies and stars and everything. So inflation is a leading theory, and many scientists, many cosmologists think it's proven, and we argue it's wrong. In fact, there are others, many other leading scientists, like many we named, like Roger Penrose, who actually one of the originators of singularity theorems and won the Nobel Prize for them a few years ago. He thinks that inflation is not really a reasonable theory, and maybe we go over all other ideas. But here's the thing: so there are a lot of myths, and we try to go over them, and we discuss what evidence there is. But we also say that it's not really mythology what we're doing, right? Because there are very precise measurements, and there are many of them. There are dozens of them that we talk about. Again, this cosmic microwave background, we talked about its discovery, but in fact, what's the most amazing thing about it, and this kind of takes us back to Fred Hoyle, because Fred Hoyle named Big Bang, but he was a critic, I mean, pejoratively or not, he was a critic of Big Bang. But I think inadvertently, he maybe gave a very good name to this theory we talk about, because bang, when you think about bang, is something loud. And our best evidence for what happened at the Big Bang is the sound waves. We cannot quite hear it with our ears, but there are ripples, variations in the cosmic microwave background that were just the sound waves, the primordial sound waves that must have been created at the Big Bang or before the Big Bang by whatever that happened there. And these properties of these sound waves are measured very precisely now. how big they are, how they change on wavelength or depend on wavelength. Now they're stretched on millions or billions of light years, so they're very, very much bigger than much longer wavelength than the sound waves we use to communicate right now. But they are there and they're measured very precisely. And any speculative, weird time travel idea you come up with has to explain them, right? And that's kind of that's why
these are sound waves that we measure now.
These are sound waves that. Well, we measure now because we exist now, but it's kind of, we measure them indirectly because, so what happened was they were propagating across the universe, but at some point, universe becomes basically low density, so sound waves kind of freeze.
Yeah, because people want to know, like, how can sound waves travel across the universe if the universe is this sort of vacuum? You need air for sound to travel.
Good. Yeah, yes. So, I mean, universe is not empty. There's matter in the universe, right? And it was dense at the early time. So you had this primordial plasma that's very high density. So sound waves could propagate in it.
Primordial plasma. And this is like a state of matter.
Yeah.
Similar to the surface of the sun.
Exactly.
Right? This kind of state where when everything's dense enough,
right,
it's the kind of thing that sound could propagate through, like throughout the whole universe, because the whole universe is like plasma.
I mean, I told you universe is like a black hole inside out. Right. I mean, the Big Bang, it's kind of like a star inside out. I mean, I guess an empty universe is like a black hole inside out. But if you have matter and Big Bang, so Big Bang is like a star inside out, like a sun inside out. So we can see the surface, right? And in fact, literally, it's the same analogy, right? So we can see the surface of the sun. We cannot see inside the sun, right? And the same as with Big Bang. We can see this thing called the last scattering surface, which is kind of the surface of the Big Bang. It's where light the density is low enough so light can propagate to us. But then beyond that, light cannot propagate directly, but sound waves can. And in fact, that's exactly the same way we can probe what's inside the sun. Of course, we have our mathematical models, but there are also sunquakes. It's called like helioseismology is a sign. So because sun is kind of very active, if there are solar flares, in fact, Phil is very good at imaging all sorts of sun-related things auroras, and then the pictures of the various.
And Phil's own images appear in the middle of the book. And I must put a link to your, like, what is it, your Flickr account or whatever? Phil is also a phenomenally talented, like, space photographer. It's like I was blown away the first time I saw it. So I'll try to remember to put that in the description as well. So yeah, but the sun.
The sun, yes. The sun is a very active place, and there are all various activity that happens. But in particular, basically, there are waves that propagate in the sun. And by mapping these waves on the surface of the sun, so these are sound waves, and also there are gravity waves that are different types of waves. By mapping these sound waves, you could actually map what's inside the structure inside the sun all the way down to the core of the sun. Which is also kind of how we know what's inside the Earth, because I mean, the Earth, there are also earthquakes, and by mapping those, because
so we're looking at the effects on the surface, the sound waves, the gravity waves, and from that we're seeing what's in the center.
That's right.
And the Big Bang is like a star in reverse.
Exactly. And that's what we do with the Big Bang. We see the surface of the Big Bang is inside instead of outside, so it's kind of inside out, but still we can see the ripples on the surface.
Yeah, we're looking at the surface from the inside.
Exactly.
That's interesting,
Yeah.
But it's the same kind of process.
It's the same idea, and those sound waves can go much deeper inside. And then there's something even more exciting. In fact, I mean, for the sun, there was something like that was a big breakthrough. There were neutrinos. This is another type of particles. It's kind of complementary to the sun. So neutrinos are these weakly coupled particles that are made at the fusion in the center of the sun. And we eventually detected them. We've been detecting them for a few decades, but they weren't quite matching until we detected all different types of neutrinos. So the key is that you want something that kind of can freely propagate in a space. For the Big Bang, there are neutrinos. They're just very hard to see, so we haven't quite cracked that nut yet. But there's also something possible, which is called gravitational waves. So these are ripples or fluctuations, basically waves in geometry. So even if there's nothing, that you could have geometry of a space according to Einstein's theory of relativity, which could ripple and wave. And those could have been emitted from the Big Bang. And there are many theories. Some of the theories of the Big Bang predict that these waves are there as well. And there are many experiments that are looking, and we have been actively looking for those. So these are all the things that can come out of, we can detect directly or indirectly from the very, very early moments, well beyond what we've seen today. And they can kind of probe these various speculative ideas and rule some of them out. And this is why it's not all fiction. There is some non-fiction in it as well. Yeah.
Phil, why is inflation an important idea? Why do so many scientists believe in it? And why are you suspicious of it? And I mean, particularly the way that we've just described inflation is the inflating of the early universe. And a lot of people will listen to that and go like, okay, I thought we knew that already. You know, the Big Bang, the universe expands. You might say, no, inflation says that it's speeding up. It's like, well, I thought we kind of knew that already anyway. You know, everyone knows the universe is expanding, and kind of who cares? Like, okay, it's faster. Well, what's the importance of this inflation idea?
Well, I think there's two reasons why it's so profound, if it's true. And we can go over reasons why it might be true and reasons why it might not be true. But let's go to the implications. One, as we said, inflation is a pre-Big Bang model. It happens before the Big Bang. So if we can confirm inflation is true, then we can tell what happened before the Big Bang.
What does that mean? Like, so what is it that's inflating?
Okay, so it's the space that's inflating.
And so this is before the hot dense state.
Yes, before the hot dense state.
So what are we talking about here?
So
Help us to visualize this.
Imagine empty space, but it's filled with a field maybe that will push the universe to accelerate in its expansion. So,
but this is not hot and dense.
No, it would be as cold as it could be. And then when inflation ends, all the energy in that inflating space actually is converted into matter and radiation. Then you have the Big Bang.
Then it's hot.
So the Big Bang is what happens after inflation. Whereas a lot of textbooks will tell you it's Big Bang then inflation. But even I interviewed Alan Guth, the inventor of inflation, and he calls it a prequel to the Big Bang. So
inflation, big, like sort of exponential increase in the size of space. Am I allowed to say that?
You can, but remember the caveats that we said before. Yeah.
And then inflation for some reason stops.
Yeah, because it's supposed to be unstable. So it decays, and this is the next most important implication.
Okay. But then the energy of that expanding space turns into matter and radiation, and that matter and radiation is the bang.
Is the bang?
Okay.
Yes, absolutely.
All right.
Yeah. But here's the other super profound implication of inflation. While this inflating in space is decaying, it's also expanding exponentially. So you could imagine it like a radioactive particle decays with a half-life. So imagine one bit decays, that's our Big Bang, that's our universe. But think about the bit that's not decayed yet. What is it doing? Well, it's exponentially expanding. So what happens is the volume of inflating space cannot go down. As long as the exponential expansion is faster than the decay, then the volume of inflating space will just go on increasing forever. So then at the next half-life, you'll get another Big Bang. Then it expands again, or the bit that hasn't decayed, it keeps expanding. So you get another Big Bang. So analogy I use is Sunday afternoon when I go to my mum's house, and she makes this fantastic chocolate cake. It's really yummy. And she puts the cake down, and we all have a slice, and half the cake is gone. Then a little bit later, we go back for seconds. The whole cake's gone. You can't have your cake and eat it.
Yes.
But imagine if the cake was doubling in size very, very rapidly. Then we went back for more cake and the cake has got bigger. So now we just have the same slices of cake that we had before, and we could just keep going forever.
So in this analogy, what is the cake? What is the thing that's getting bigger and bigger?
It's the space, the inflating space.
The inflating space. And our universe is not that inflating space.
No, it's what came when that inflating space decayed into matter and radiation.
But so help me picture this, right? So we've got inflating space. This is inflation. You've got space sort of getting bigger.
Yeah.
And then inflation stops.
In our patch.
But so you've got this sort of big inflating space.
Yeah.
And it's just a little patch of that inflating space that stops inflating, which causes this boom, like energy, matter, all this kind of stuff.
Yeah.
But the whole thing is still expanding. And so that little miniature part is expanding locally as well.
Yes.
But outside of that,
it's expanding even faster.
And there might be other patches that keep stopping and slowing because inflation is unstable.
Yeah.
And so there are little patches where it stops, and that's vroom, 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 big bang, big bang, big bang, maybe little bang.
Yeah, that's what most inflationary cosmologists suggest.
So does that mean that this inflationary idea points to a multiverse?
Yes.
That what we're talking about?
That is where the idea of a multiverse comes from. I mean, there's another view from quantum mechanics, but that's generally considered quite separate.
Yeah, sure.
But this idea of the multiverse is coming from inflationary cosmology, and that is quite mainstream.
I'm often told that the only reason people believe in the multiverse is as a way to get out of like the fine-tuning argument for the existence of God. In other words, like the multiverse, like we can't say it's false, it's ridiculous, and we're not going to say it's ridiculous, but there's no evidence for the multiverse. It's essentially like a philosophical tool that people use in religious arguments, but not the case?
No, definitely not the case. I mean, it was a discovery. It wasn't. Someone didn't look at the fine-tuning argument and say, well, let's have a multiverse. No, what happened was they were looking at inflationary cosmology. And then it was actually Nia Esh's colleague at Princeton who was one of the first to realize that inflation would make a multiverse. This is Richard Gott. He's also the master of time travel. He's an expert on time travel and lots of things. So he was one of the first to say, inflation would just make a multiverse. But at first it was thought, well, these are sort of curious solutions to inflation. They didn't really take it very seriously. Then another scientist came along called Alex Valenkin and Andre Linde as well. And they showed that this was a generic property of inflation. So Alan Guth, there are actually lots of different inflationary models, but what Guth says, he's the creator of inflation, is that almost all models of inflation are eternal. So they will make a multiverse. So independent of any argument about fine-tuning, we have an argument for a multiverse coming from inflation. So if you take inflation seriously, then it looks like it generates a multiverse. Now, there are one or two cosmologists, Slava Mukhanov's one, that don't agree with this, but I think I've interviewed a lot of the people that worked on inflation. I would say that's a consensus view, that if you have inflation, then you have a multiverse. And then we can ask, is there evidence for a multiverse? And that depends on your view on whether there's evidence for inflation, because a lot of cosmologists say there is evidence for inflation. In fact, they think it's very strong evidence. Some people say it's been proven. And what we argue in the book is, well, there's good arguments back and forth about this. You can say, inflation made lots of predictions, but then you can challenge that and say, well, maybe that's a dubious statement. So, I mean, I think Niash is more in the anti-inflation camp, whereas I change my mind like every other day about this. Sometimes I think the inflation is really strongly supported, and others times I'm with the critics.
I think Phil has to be very diplomatic because he interviews all people. So I can be more strongly worded. But in the book, we try to find a common voice so that no one gets offended.
Sure. To be clear, Alan Guth is not the creator of inflation. He is.
No, he is.
He's the guy that came up with the idea, but he's not the man who
he came up with the idea.
Who created the inflationary universe.
Well, we do talk about whether it's possible to make a universe in a lab.
That's the other thing, right?
And Alan Guth is one of the scientists who suggested that it might actually be possible.
Okay, look, I want to talk about that.
Yeah.
But also, I want to take a moment because, like, you guys have been writing about this for it must have been years now, like on this particular book, and before that, a long time. The series you're referring to, Before the Big Bang, which is on YouTube, it's on your channel, Phil, which I'll also make sure is in the description if people want sort of a documentary version, I suppose, of this book. And you're so wrapped up in it, I think, that when you're talking about these models and inflation and stuff, it's exciting, but we've got to take a step back and realize that people are listening to this with no idea what we're talking about, right? So they're like, okay, so let me get this straight. There's this idea of like the Big Bang. Okay, the terminology we should use is that the Big Bang is whatever the hot, dense state is at the beginning of like our observable universe. There may have been some stuff existing before that, this sort of like empty space that is expanding and expanding in such a way that there are little local patches of, creations of like mini universes everywhere. There are going to be a few questions that come to mind. Firstly, so what is this like thing that's expanding? What is this empty space? It can't be empty if stuff is like coming out of nothing. There's got to be something there that's expanding. Secondly, we talked about like inflation stopping because it's unstable. Not really sure what that means, but the thing that really gets me is like, okay, there's empty space and it's expanding, and then it stops, and then vroom, like matter and energy, just like what, out of nothing, out of nowhere, like, you know what I mean? Can we take a step back now that people understand what we're talking about? This big sort of space that expands exponentially, potentially, and little pockets of instability, and so like people are going to be like, but what is this? What are we talking about? How does this matter and radiation spring up? Like where are we? Where's this coming from? You know what I mean?
So imagine like a pool table.
Yeah.
Okay. But imagine like there's a hole like in the middle somewhere, right? And so imagine there's no friction. Okay, sorry. I should not imagine too much. Okay, so imagine there's no friction. So there's like kind of imagine you can hit the pool ball and it just keeps bumping left and right and is all over the place, right? So that's kind of like a quantum C, or if you want. So that's the pool table is your inflation. It's like the universe somewhere in there. Every now and then it may come across this tiny hole and fall into it, and then that's where it ends, right? But it's the thing is that this ball doing different. I mean, the state of the space doing different things in different places. They don't talk to each other. It's an infinite universe, right? So some places in the universe, this ball may fall into the hole, and that's where you get a Big Bang. And then you can kind of see when the ball falls, then it's kind of you make it hits up, right? So that's that again is an analogy. You shouldn't take it too seriously. But what you're doing is that there is energy in empty space, right? And this is the important thing is repulsive gravity is not such a strange thing. In fact, any kind of energy that you associate with empty space is going to give you repulsive gravity. And the simplest model for dark energy we have now is energy of empty space, the so-called vacuum energy. And it could have been the same with the inflation. It's just that a much heavier empty space. The vacuum energy during inflation would have been much higher because there were much faster expansion, much faster repulsion, or much stronger repulsion. But still, what happens is that so universe is basically is inflating. This is your pool table. Anywhere in there, there's this huge vacuum energy, and universe. You think it's vacuum, nothing is happening, but vacuum in quantum mechanics is actually a very vibrant place. There's a lot of fluctuations that are happening. Things are moving around. So, the ball in a pool table moving around, this is like a classical thing. But really, all the fields in a space are vibrating like very violently in quantum mechanics, basically.
So this empty space is this sort of ocean of quantum fluctuations.
Right, exactly. And that's everywhere, right? But the thing is, the instability, the idea of instability is that it could be, and it doesn't have to be, but for Big Bang to happen, there needs to be an instability. There needs to be a hole somewhere where inflation needs to end. So in your big pool table, if your ball, which is kind of the state of your space, or your field, if you want, is called fields, I guess, instead of billiard balls, we call them fields in physics. So if your fields come across this hole, they may fall into it, and that's where kind of they heat up, and then you create matter and radiation and stuff. But this is something that happens kind of randomly, stochastically, and it doesn't have to happen everywhere because it just is a random fluctuation. In some places it happens. Those places you make a pocket universe, and we happen to live in one of those pocket universes because we cannot live anywhere else. Like in this vast sea on the billiard table, there's nothing there. There's just vacuum, right? So we need matter and radiation and kind of we need fluctuations to actually grow. We cannot live in vacuum.
Okay, so this empty space that's expanding and inflation is not truly empty in the sense that it contains sort of quantum fluctuations.
That's right.
And some of these fluctuations sort of pop matter and energy into
That's
existence.
right, yeah.
Okay. Inflation then, I'm imagining before our Big Bang, we've got this space that's growing. Does that mean that if I play that in reverse, that empty space of quantum fluctuations and stuff would shrink, meaning that eventually we still have to get back to this like singular point from which everything expands? It's just now instead of talking about our universe, we're talking about this empty space of quantum fluctuations, which is not actually nothing. Right, Phil?
Well, okay, so there's a big question. So inflation is often called eternal inflation because once it starts, it can never stop. It will make universe after universe after universe. Now, there's a question, okay, it's future eternal, but is it past eternal? Can it just go back forever? Remember, Nietzsche said that one of the assumptions of the singularity theorem that proved the beginning of time was that gravity is always attractive. Now we're talking about repulsive gravity, so we violate the Penrose-Hawking theorem that proved the Big Bang was the beginning. So maybe we don't need a beginning anymore. Maybe inflation is past eternal as well.
But surely something is, if we're thinking about going backwards in time, if something is shrinking.
But remember, the whole universe could be infinitely big. right? So when we said shrinking, it was only a particular patch that we're concerned of. The equivalent of us in this room of what we can see.
So inflation is not like a thing that happened and it's now over and done with. The idea is that inflation is like the status quo. That is like that is just what's going on.
The majority in this scenario, the majority of the universe is inflating.
And that never ends. It's just inflating, which is exponential growth.
Yes.
And that just keeps going forever. And maybe it's past eternal.
So that's the debate. Is it past eternal?
And little universes sort of pop up here and there.
People often quote a theorem by Borda, Guth and Vilenkin.
Yeah.
And that says that inflation cannot be past eternal. However, other scientists have said actually it can be past eternal, that they made mistakes in their mathematics or they made some assumptions. And so maybe it can be past eternal. And obviously we can't tell. There are claims that inflation is verified empirically. And we can debate those claims. Is that true? Is that false? But nobody would claim that we could empirically check whether inflation is eternal into the past or not. That's something only we can investigate through theory. And unfortunately, theorists don't agree about this. So we don't know whether inflation would be past eternal or not. But, if you believe Borda, Guth and Vilenkin, then actually inflation would have a beginning. So then you could ask, okay, well, what happened before inflation?
And what would that question look like? Because now we're not looking at this hot, dense, big bang matter and energy. We're talking about the beginning of inflation, which, as far as I understand, is something which applies to this quantum soup, for lack of a better word. And that would therefore have some kind of beginning. Like, I don't know, man. Like, is there time in this inflating quantum soup? Because I thought that time was like a dimension of space, and if space is part of our universe, like, does that apply outside of it? Like, I'm struggling to like visualize it. I'm visualizing almost this like fabric expanding. It's a bunch of like lines going through space that's growing and growing and growing, and it's full of quantum fluctuations. Does time pass in this inflationary universe, for example?
Okay. No. It sounds that there is these all sound very mind-boggling and science fiction-y. But in fact, the physics of inflation is like the most conservative kind of physics you can find. So there is time, there is a space, there is energy. Everything kind of works in the way that Einstein thought it would 100 years ago or so. Now, there are quantum fluctuations as well. Quantum fluctuations, I guess famously, Einstein said that God doesn't play dice. So he had like a mixed relationship, a conflicting relationship with quantum
that's
mechanics.
A famous quote, Einstein saying, God doesn't play dice with the universe. I only found out from your book that Niels Bohr, responds by saying, Einstein, stop telling God what to do.
Right. That's true. Yep, indeed. But these are all like 100-year-old ideas. You're just kind of pushing them to the extremes. And I think that's what gives you this idea of multiverse and inflation. So in fact, these are not the most radical things we discuss. This is the most conservative thing we discuss in the book. It's as mind-boggling as this sounds. Because basically it's just saying that, yes, early times, there was this huge vacuum energy. But vacuum energy, again, it's something, a standard quantum theory can give you a vacuum energy. Now, may not give you the right amount of vacuum energy, but it can give you a vacuum energy. It just that you had a big vacuum energy early on, and there are fluctuations around it. There's regular time, regular space. So I think everything works in the most conservative way possible in eternal inflation. It's just a very weird different place because we are pushing the laws that we know to the extremes that are very unfamiliar to us or unfamiliar to the universe as we know it today, right? But the more mind-boggling things are, for example, if the entire space, time didn't exist at some point, and that's a separate scenario. For example, Hartley and Hawking proposed that maybe inflation was not eternal. It actually started, maybe time started at some point. And it's actually, very reasonable point is that because we know we want a theory of quantum gravity, we know quantum mechanics and gravity, at some point they're going to come to head. So what does it mean and how does it look like? And one way it may look like is that maybe at some point time, which is essential part of theory of relativity, because relativity is a theory of space and time. Maybe time doesn't exist at some point. At that point, at this time in the classical sense that we know. So I think the analogy I like that Phil uses is like the wetness of water, right? So we all are familiar with wetness of water. But if time is like wetness of water, that fundamentally it doesn't mean anything, right? Because the water, if you could look at it with a very powerful microscope, is just made out of molecules, right? There is no fundamental concept of it. It's just an emergent concept. So what if time itself is an emergent concept? And right now there is a reasonable definition of time, but if you go back at some point, that just ceases to exist.
What does it mean to say that there is, like, time begins at some point? Like, it seems to me that in order to say at some point, you need to sort of place it on a timeline.
Right.
If you're talking about the beginning of time itself,
Right.
like what could that even mean? I mean, trying to place the beginning of time at a point in time.
Right.
It's like trying to place the origin of all matter in a particular location or something. You know what I mean? What could it mean to say the beginning?
Well, I mean, I think you could try to be precise about it, but I mean, you can say, okay, so when you're asleep and awake, right? So where is the exact point where you go from being asleep to being awake? And I think it's, I mean, we could try to define it more precisely if we have a precise theory, but it kind of tells you that, I mean, if you think about it, we have experiences, and in physics is the same. I mean, everyday experiences, we don't necessarily quantify it when we are asleep or we are awake. I mean, I suppose physicians can quantify it, like take our pulse and say, okay, so this is asleep, this is this exact point is where someone falls asleep. But that's not really the point. The point is that we have an approximate description of something, and that approximate description might be good, like when now you and I are talking. But at some point, that approximate description, the way I understand the word, gets kind of more and more fuzzy, right?
But my issue isn't trying to figure out like when time began. My issue is just with the concept as a whole, right? Because if I imagine that there's a point, if we go back and back and back, there's a point at which, you know, time stops, time doesn't exist anymore.
Right.
I'm sort of imagining being at that point where there's no time. If there's like no time, like that means sort of we're existing timelessly. How can we then say, okay, there's no time, no time is passing, and then at some point, time starts? You know, surely if it's timeless and the universe doesn't exist yet, and it's timeless, then the universe has to timelessly not exist. How do you get this beginning of time at a point in time? You get what I'm saying?
Well, one definition of time, I don't know if Neil agrees with this, but one definition of time that one physicist said to me was that it's a correlation between events. So if you don't have correlations between events, there's no time. But that doesn't mean there's nothing happening. So things could be happening even if there's no time, because there's no correlation between events. You can't make a clock.
This will depend on your theory of time, right? So people are probably broadly familiar with the A and the B theory of time. I spoke to Emily Cressy-Hurst on the show the other day, who helped to introduce me to the concept of the C theory of time, which, if the A theory of time is that time really passes and the past doesn't exist anymore and the future doesn't exist yet, and the B theory of time is the block universe where the past and the future all exist, and, you know, we're sort of somehow privileging a particular moment, but the past exists and the future does too. The C theory of time is that, like, there is just the relation of events, you know, and there's no direction of time. And she sort of said, like, you know, to have time, you just need to know that you have like World War II and you have like this podcast, and they are like related to each other. There's no sense in which there's an objective direction. There are just relation of events. The only thing that matters is that they're in the right order. So it doesn't matter that, like, you don't need to say that one comes after the other, but you can't put the death of Queen Elizabeth like outside of that. That has to go in between them, but time sort of isn't passing in the traditional sense. Okay, so we've got this like relation of events as being just the nature of what time is. So if people are struggling to imagine, like, you know, they're sort of thinking, well, how can there be a beginning of time? That doesn't make any sense. It's like, just try to think about the concept of time now when it does exist. Try to define it. Try to understand what it is and how it works and what it means. That is confusing enough. So, like, I do think it's like a really difficult challenge to be thinking about the beginning of time, but maybe that's just a property of the weirdness of time as a whole. But okay, so maybe time has a beginning, but stuff is happening before time begins.
There could be, we can't help but use this word before, right? Because it's part of our lexicon and we're used to the familiar world of our experience.
Sure.
But the early universe is nothing like the world of our experience. I think that thing, all of the different models would agree on. So forget about your everyday world. The Big Bang is going to be very, very different. And there are different notions of time within physics as well. So another is what's called conformal time. So an analogy here might be, imagine you play a chess game.
Mm-hmm.
So when people play chess, you might see them writing down the moves.
Mm-hmm.
And you could put those moves in a sequence and you could say, well, it was 6 seconds elapsed between that move and that move. And maybe I had to think about this one. So there was a minute between this one and this one. And conformal time would keep the order, but it would lose the scale. And Roger Penrose has a cyclic model of the universe that Nia Ayesh has built upon. And this says, well, there's still conformal time, but there isn't the sort of normal time that we experience. So we don't have the scale of time, but we still have a sequence of events. So he has a cyclic universe that loses its sense of scale because it turns out that in order to have the time that we're familiar with, you need to be able to build a clock of some time. And I don't mean a clock like, my watch, but anything that could tell the time. But if there was no mass in the universe, which may be true in the Big Bang, it might be true in the far future, then you couldn't build a clock. So you would lose our normal sense of time, but you could still have this conformal time. So a very, very different notion of time.
Here's a problem, Phil. As you well know, right, if we're imagining this eternal inflation, so time sort of stretches back infinitely. We've got our little pocket universe, but everything else just sort of goes back infinitely and there's no beginning. As you well know from the study of the philosophy of religion, this is not possible, right? We cannot have an infinite past. A lot of people think that an infinite past isn't true because of the Big Bang and science, but okay, maybe we can't be so clear on that. But philosophically, we can know it, right? Like William Lane Craig talks about this all the time. Al-Ghazali proved this by just thinking about, the fact that, for example, if the universe, by which I mean the whole universe, is past eternal, then there would have to be an infinite number of events in the past, which means that there would have had to have elapsed an infinite number of events before we got to today. But you can't surpass an infinite number of events because it's infinite. And so if the universe is past eternal, we would have had to transgress an infinite number of events to get to today, which you can't do. But here we are at today, which means that the universe can't be eternal, right?
No, not correct, I'm afraid. I've actually made a documentary on this Kalam cosmological argument on my YouTube channel and interviewed lots of philosophers, including religious ones. And I think it's widely rejected, this argument. So let's see what's wrong with it. The idea is, well, if you start counting 0 today, 1 tomorrow, 2 the day after that, you're never going to get to infinity. But if the universe is past eternal, then we would have had to have got to infinity. And it's certainly true that you can't get to the end of anything that's endless. That's right. But that doesn't mean you couldn't have an eternal past, because if the hypothesis is that the universe had a beginning, then there is no starting point. There's not a moment where you start at 0 and then go 1 tomorrow, 2 the day after. Rather, there is no starting point.
If the universe had no beginning.
If it had no beginning. There is no starting point. So a lot of these analogies that are used to try and prove that the universe can't have a beginning sort of assume that there's a starting point infinitely far in the past, and then you start counting from there. And the idea is you can't get to infinity by just counting. I think what they're kind of assuming is that if you start with finite and you add more finite, you're just going to end up with a bigger finite number. You're not going to have an infinite number. But the whole point of a universe that's eternal into the past is that you don't start with finite. It's always infinite. So this problem simply doesn't arise.
So you understand the grammar of the problem, right?
Yeah.
Which is that, okay, so there's no point at which you can start counting. But that's kind of the problem, which is that future events happen after the past ones. Past events happen before present and future events. And if there are an infinite number of past events, and the future events have to come after that, you understand the problem with imagining that somehow there just have elapsed in the past an infinite number of events. It sort of seems like we're at the end of this chain. Like, how should we be thinking about it? Because the only other way I can think about it is like me right now looking infinitely forward and infinitely back. Oh, that makes sense. So you start with today, which is 0, and the past is more like -1, -2, -3. So there's no beginning to the past,
Yep.
and there's no end to the future. Sure.
That
But
makes
then that
sense.
seems to sort of metaphysically privilege the present, like me right now. Like, why is now 0? Well, it's not anymore because time's just passed. So maybe now is 0, and 0 sort of moves with me, which means that if all human beings died, there'd be no way to have that sort of privileged 0 position from which to sort of look forward and back. So without sort of arbitrarily picking the present moment as our starting point, like objectively, there's no way to even start like counting at all. There's no way for me to count today and tomorrow and because there's just no starting point. You know, like it's just like impossible to wrap our heads around.
Why would you say it's your privilege if everyone else sees the same thing that you see?
Well, for a few reasons. Firstly, because it's not clear to me that like everybody else is seeing the same thing as me because time doesn't move linearly, right? So my 0 wouldn't be the same as your 0.
Yeah.
But also just like metaphysically, right? Like, I mean, like if we're talking about the actual nature of the universe, which means that it's easy for us now, alive human beings, to sit here and go, okay, well, let's just consider now as our starting point for our knowledge. And our knowledge stretches infinitely forward and infinitely back. And there's no problem with that, you know, no beginning and no end. Cool. But in order to have that starting point of now, we need to exist. We need to exist in time to think of it in those terms. If there were just like no human beings, if our universe never popped into existence, or if we all just died, there'd be no conscious agent to say, all right, now is the present and we're going to think forward and back. But there still would be like an answer to the question of whether the universe had an infinite past or not. But there'd be no people to pick sort of 0 as the present, right? Because there'd be no one experiencing the present.
Right.
There would just be an answer to whether there have been an infinite series of events or not. You know, I don't really know how to wrap my head around the idea that past events come before future events, and yet like we can sort of stretch that infinitely. Right?
Well,
like,
I think we can all agree that this is hard to get your head round.
Yeah.
And it's true whether the universe had a beginning, that's hard to get your head round.
Yeah.
Or whether it didn't have a beginning,
Yeah.
that's also hard to get your
Sure.
head round. And I think it was the philosopher Kant that said that he could prove that the universe couldn't have a beginning and that it must have a beginning, right? Because it's very, very difficult to think about. So I think we can all agree on that. But this idea of now, of course, in relativity, there is no unique now that the universe has to get to. So I think this is not something that we have to worry about. Now, could the universe be eternal into the past? There's no contradiction with that. Now, some people say there's actually a contradiction. You know, William Lane Craig.
Yeah, like the Hilbert's Hotel
Hilbert's
thing.
Hotel.
Like
So
anytime you introduce the concept of infinity, it leads to paradoxes.
Well, what it leads to is counterintuitive answers, but they're not actually contradictions. So let's take an example of something that's claimed to be a contradiction and try and show why it isn't. So people may be familiar with this notion of the Hilbert Hotel. This is going back to the mathematician David Hilbert. Although, ironically, it was the physicist Gamow, who was one of the defenders of the Big Bang, who used Hilbert's Hotel and popularized it, because I think Hilbert mentioned it once in a lecture and that was it.
Interesting.
And what Gamow was trying to say was, look, the universe could be infinite and expand. Because it sounds really strange. Well, if it's infinite, how could it get any bigger? But he said, no. Hilbert's Hotel shows that it can. So in fact, the universe, and he was trying to say, look, the universe could be infinite and expand. So
Hilbert's Hotel is the idea of this hotel with an infinite number of rooms, right? There's just like an endless number of rooms. And every room is occupied. And so somebody shows up to the hotel and says, I'd like a room, please. And they go, sorry, every single room in our hotel is occupied. And they think, well, actually, I've got a solution to this. All we'll do is we'll take person in room number 1 and we'll ask them to move to room number 2. Person in 2 moves to 3, 3, 4. So everyone just moves one number up. And because there are infinitely many rooms, there's always the next room that a person can go to. So we say, okay, we got a room for you. And they put them in room 1, which seems like a paradox because every room is full, and yet there is a room for every single tenant to sort of move into. And so the William Lane Craigs of the world look at this and say, that's a paradox because the place is full. He always says, it would have to say, you know, what is it? He says, like no vacancy, guests welcome, you know, on the front, something like that, which is a paradox. But are you telling me then that this is sort of originally formulated as a way not to say, look how counterintuitive this is, so it's impossible, but rather look at how I can prove the possibility of this really counterintuitive thing that infinite things can expand.
Yeah, that's exactly
awesome.
why it was popularized.
Hey, cool.
I mean, Hilbert didn't think about this, but as I say, I think my understanding is he gave one lecture about it and never mentioned it again.
People so often like it's so interesting how these ideas embed themselves into popular culture, sometimes for the complete opposite reason. Like you mentioned Schrodinger's cat earlier, Nayesh, which a lot of people think, they're like, I've heard of this. Doesn't quantum mechanics prove that the cat is dead and alive at the same time? Not realizing that Schrodinger invents it as basically a way to mock this interpretation of quantum mechanics. To be like, look how ridiculous this idea is. But the way it's embedded itself in popular culture is like, oh, look how Schrodinger like proved that the cat is dead and alive at the same time. It's like completely on its head. And maybe this is another example of that.
Yeah, this was an attempt to prove that we could have an infinite universe.
Right.
And let's just go
that still expands.
Yeah, that still expands. Yeah, so let's just go to the sort of notion that it leads to a paradox or a contradiction.
Yeah, sure, okay.
So two things. One is the paradox of how can a hotel that's full accommodate new guests? And we're used to our intuitions that say, well, that's impossible because the universe that we know, all the hotels have a finite number of rooms. So, of course, they will eventually run out of space. But an infinite hotel simply cannot run out of space. There's always the next number. So it's an equivocation on the word full. If what you mean by full is someone in each room, then yes, the Hilbert Hotel can be full. But if what you mean by full is can't admit new guests, then the Hilbert Hotel cannot be full. It can never be full. So the Hilbert Hotel can always admit new guests. Now, the other thing that's claimed is that there's a contradiction, because let's suppose we take out all the even number of guests from the Hilbert Hotel. How many have we got left? Well, we've got infinitely many. So we took away infinitely many and we've got infinitely many left. So infinity minus infinity is infinity. But now let's say all the guests in room number 4 and above check out. Now we've taken infinitely many guests out, but we've got 3 left. So infinity minus infinity is 3. So it looks like Anna Craig in a video said this is a contradiction.
Yeah, because from that you can derive that, 1 equals 2.
Yeah, exactly. But this is just wrong because infinite sets have different properties to finite sets. So in a finite set, you don't have to specify like which thing you took away. So there's a table in front of us now. There are 3 cups in some sense, 2 glasses of water and a cup of coffee. Was it, Alex?
It was, yeah.
Right. Okay. So if I said, right, there's 3 of these things on the table and I take 1 away, you don't need to know which one, whether it was one of the glasses of water or the cup of coffee away. I take 1 away, there's 2 left, right? But for infinite sets, you have to specify which things you took away. So once we specify which things we took away, well, we didn't do the same operation. When we took the even number of guests away, that's one operation. When we took all the guests in room 4 away, that's a different operation. They are not.
You can't just say
same.
Infinity. You have to specify it's like the difference between saying, okay, so there's a coffee and 2 glasses of water on the table. If you say, okay, well, if I take 1 away, I'm going to take this glass away. How many glasses of water are we left with? 1. Okay, right, let's go again. Now I'm just going to take 1 away. This time I took the coffee away. So how many glasses are left on the table? Well, there are 2 glasses of water on the table now. So in both cases, I've taken 1 away, but one's given us 1 glass of water and another has given us 2 glasses of water. Yeah, because it depends what you take away. You can't just take away 1. You have to take away 1 of something. You can't just take away infinity. You have to take away a particular set of infinite things, a particular kind of infinity, right?
Yeah, so infinite sets have different properties to finite sets. And I think the power of this argument is that it carries off your intuitions about finite sets. And you think that the finite sets must have the same properties as infinite sets, but they don't.
Okay, Nayesh, what's your thoughts on this? What do you think about the plausibility of an infinite past? Do you place stock in it? Do your intuitions scream at you that there must be a beginning?
Yeah, I mean, infinity is all over mathematics, right? So it's, all this stuff, I kind of, we talk about it at high school or middle school or whatever, but you don't do stuff with regular infinity that you do with regular numbers. It's just, no. It's a perfectly fine part of math if you know exactly where it comes and what to do with it. When it comes to physics, again, we build physics using mathematical language. So same places that there's infinity in math, there's infinity in physics because it's just the same thing, right? But then the question is, so where are the places in physics where infinity cannot be? And if I'm measuring something like I'm measuring the time or temperature in this room or anything I measure, it doesn't make sense to say that I measure infinity. So those are the places where infinity is not allowed, because that's not a real number. That's not a measurable number, right? Anywhere else, it's fair game, because I mean, as long as it appears somewhere that it's not directly prediction of a measurement, and I can still do my predictions, like I can make calculations, right? There's really no problem with infinity. So as long as I have a way of dealing with it, right? So that's the thing. Now, that being said, having an infinite time is kind of rubs me the wrong way, because it's kind of the same as a multiverse, right?
Mm-hmm.
As you're saying that, okay, there's an infinite universe, infinitely many pockets with various properties I don't have access to. It sounds like science fiction, but also it kind of feels that it goes beyond the realm of physics, because I cannot really constrain them, and there's no testable prediction. And of course, this is a controversial topic, an exciting area of debate, that, okay, this multiverse testable or not, and we do talk about some of the potential ways of testing it. But I mean, for the most part, it's either untestable or very hard to test. Infinite time is kind of the same, right? This in my view, because if there are things that happen a very long time ago, like long before the hot Big Bang that we see, I mean, were they there, were they not there, doesn't matter. So we could talk about it from a mathematical standpoint, but is it part of our physical language, or should it be part of our physical language? And that's the part I'm kind of more skeptical, which is, it kind of goes hand in hand with this skepticism, eternal inflation, and multiverse. So my own favorite, so I think we talked about Hartle-Hawking model, where there's time begins to exist at some point, didn't exist before some time. We worked on a different model called holographic cosmology with Kostas Skenderis and others.
Holographic cosmology.
That's right, holographic cosmology. So holography is this very, very exciting part of theoretical physics, which actually came out of a string theory in the past 30, 40 years. And the idea is that maybe if you want to describe gravity in a quantum sense, you shouldn't think about gravity in a space and time. You should kind of think about boundary of the region and think about quantum mechanics in the boundary. So there is this idea of holography that really understanding gravity is like understanding quantum mechanics in one lower dimensions, which is like holograms. It seems like you see something three-dimensional, but it's really two-dimensional. So one way to describe it is that maybe one of our dimensions, it could be one dimension of a space or one dimension of time, is kind of an illusion.
Okay.
Yeah.
Pause. So
Yes.
a holograph.
Yes.
People are familiar with these things. Like you get them at little stores on the side of the beach or whatever. It's a 2D plane, but it kind of looks 3D, right?
That's
you
right.
look at it from different angles, and it shifts and it moves. It is actually 2D.
It's actually
but
2D.
It has the appearance of 3 dimensions as we sort of move around it.
Yeah.
The idea of holographic cosmology is the idea that one of our dimensions of time, or one of our dimensions of space, or maybe the dimension of time, works in a similar way. That there's actually only 2 dimensions, and the third dimension is a holograph, or there's only 3 dimensions, and the dimension of time is a holograph. And
That's right.
Therefore, like an illusion. This
is a good question. So now, illusion is a kind of depends on your definition of reality, right? Now, our three-dimensional kind of description in this room, we're talking, we're moving around, up, down, left, right. We can wait, so move forward in time. So that description of 3 space and 1 time works very well. Okay, so you may think it's an illusion, but it's a very good illusion. Like, it's a very, very convincing illusion, right? There might be a different description of this room without 1 extra dimension. You could imagine it exists. It's just very contrived and a strange description of these events that are happening if you don't use, say, 1 of the dimensions, right? It's possible, right? But it's just not very convincing illusion, right? And the idea, this idea of holography is that really there are 2 ways to describe things. One of them might be easier, at least in some language, in the language that we're familiar with, but that depends on the situation. Right? And we know there are situations where this three-dimensional description becomes very contrived, and those are near singularities, right? So these places where quantum gravity plays a role, where basically there are strong fluctuations in geometry. You could have black holes popping in and out of vacuum. You have very strong curvature. So these are places where we really understand we need to understand quantum mechanics and gravity playing together. And right now we don't. So in such situations, in fact, a more satisfactory, more kind of simple to describe language is a language without one of those dimensions. Now, this dimension you're taking away, it could be a dimension of time or it could be a dimension of space. And depending on the setup, the problem you're trying to solve, the kind of singularity that you're dealing with, it could be a dimension of a space that is easier to take out, or a dimension of time. And for the Big Bang, this holographic cosmology, the idea is that when you get close to the Big Bang, or Big Bang singularity, if you want, so past the hot Big Bang, maybe, close to Big Bang singularity, this is where this 3 + 1 dimensional description breaks down, and maybe you just have 3 dimensions of a space. No dimension of time. No dimension of time.
Just dimensions of space.
Just dimensions of space. So that's an example of basically you have regular time all the way down to some point, and then at that point, it's not that the time stops to exist. It's just that your description, your stories in terms of time becomes more and more convoluted.
Is this a version of time being like an emergent property?
That's the idea. So in this case, time would be emergent.
So as you go towards the Big Bang, it gets to a point where it's not that time ceases to exist, but you're operating on a level where this holographic illusion, if you like, of time, it just sort of doesn't apply in the same way that temperature is an emergent property, in that like things are hot and things are cold. But if you go small enough down into the atoms, you realize that temperature is just atoms vibrating, and an atom vibrating is not hot or cold in itself. You have to zoom out before you get this concept of temperature, which is emergent. You know, a cake is spongy, but if you zoom in and look at all of the atoms it's made of, none of the atoms are spongy. You have to zoom out, and it's not like when you start zooming in with a microscope to this cake, sponginess just disappears. You're operating on a level where it just hasn't emerged yet. And time might be a property a bit like this, where not so much zooming in, but going backwards towards this Big Bang singularity. Time as an emergent property just sort of doesn't apply here, or something like that.
This is an excellent analogy. In fact, we have a technical word for exactly the zooming in and out. It's called holographic renormalization.
Holographic renormalization. I prefer the cake thing.
Well, I mean, Phil has a video about holographic renormalization.
Yeah.
I think
Phil's got a video about everything.
That's right. Yeah.
So is this how, like, I mean, one phrase that we often hear, especially in like popular apologetics and just general sort of discussion, is that the laws of physics break down at the Big Bang. And this often is used to indicate this impenetrable epistemic boundary that we sort of can't really discuss or talk about the Big Bang scientifically, because that's where our laws of physics break down. Is that true? Is there a sense in which that's true? And if it is true, does it place the Big Bang like outside of scientific apparatus, if science relies on laws to sort of explain the universe, and these laws break down at the Big Bang? You know what I mean? I mean, it sounds a little bit like when time stops existing, it sounds like, you know, physics beginning to break down. But I don't know. You must have heard this language before.
Yeah, of course.
Do you think it makes sense?
I think the case is that it's general relativity that breaks down at the Big Bang.
Interesting. Okay.
So it's not necessarily the laws of physics break down, but rather the laws that we have break down. And what people like Nia Ayesh and other cosmologists are trying to do is to expand what those laws are, to sort of give us new laws, in the same way that we had Newtonian physics and then Einstein gave us new laws. But it wasn't that new laws came into existence. As you pointed out, Alan Guth didn't invent, the inflation. He invented the theory. So this is what physicists and cosmologists are trying to do. They're trying to discover the laws that actually hold at the Big Bang. So Stephen Hawking famously said, that in his no boundary proposal, the laws of physics would hold everywhere. There's nowhere where the laws of physics break down. So this is what we're trying to do. We're trying to push our envelope of knowledge to go beyond that point where they break down. And this is where the controversy is. And this is what the battle of the Big Bang is all about, because we don't know what those laws are. There's lots of proposals. There's string theory, there's loop quantum gravity, holography, all kinds of ideas. And so we don't know which is the right law to use. But that doesn't mean the laws themselves break down. They may always exist.
That's interesting. I mean, I kind of wanted to get to this in a moment because I wanted to talk about universes coming into existence out of nothing. But like, Vilenkin has this idea of universes that can pop into existence out of nothing. And in your book, you talk about how there's this criticism that you've made to him in your video that this would require these laws of physics to like exist before the universe came into existence. Because if you imagine like the universe cropping into existence from some quantum fluctuation, that means the laws governing quantum physics must predate the universe. And Vilenkin says that he just thinks that the laws of physics just exist like as a platonic object. They're just these things that just definitely exist. That's definitely not my view of the laws of physics, but it does lead to this interesting question of like, it does seem like there needs to be something exterior to all of this, right? Like, I would say that even if the universe were past eternal, there's still a good argument to say that it requires some kind of sustaining cause. And this is something which someone like Aquinas agrees with. Like, I think Aquinas thought that the universe did have a beginning, but he also said that even if it didn't have a beginning, it would still need some kind of cause. So maybe I can begin by asking, and maybe this is a question more for Phil, I'm not sure. If the universe did have a beginning, if we did know that it did have a beginning, right? Either the beginning of universal inflation, or there is a Big Bang singularity or something. If it did begin to exist out of nothing, do you think it needs a cause?
Personally, my opinion is no. We certainly can't demand that it must have a cause.
Okay.
Let's just unpack what we mean by a universe from nothing here, because there's different notions of that.
Yep.
So one you mentioned was it was coming from a quantum fluctuation of the vacuum.
Yeah.
And it's an older idea of a universe from nothing that goes back to Edward Tryon. And when people sort of make criticisms of the idea of a universe from nothing, they say,
that's not nothing.
That's not nothing, because that's a vacuum. And Neil Ash talked about the vacuum is not nothing.
Vacuums can't be
It's
nothing.
got all kinds of activity in it. But what Vilenkin suggests is something quite different. Here the idea is, well, what if we treat space-time or space itself quantum mechanically? Then his idea is that space itself would fluctuate into existence. So it's not coming from a vacuum.
So where's it coming from?
In his view, it's coming from a state with no space.
Okay, so just to be clear, when I say nothing, I'm talking about, like, as Aristotle said, what rocks dream of. I'm talking about what you see out of your elbow. I'm talking about nothing, right? And it like, even to say from nothing, the way that I've pictured that in my head is I imagine sort of darkness and then something pops into existence. But no, there's no space, there's no extension, there's no anything.
But that's right. In Vilenkin's model, there is no space. The way you can think of it, you've been involved in philosophy of religion, Alex, and you'll be familiar with the idea that God created the universe ex nihilo, no materials. So that's what we're talking about here. It's exactly analogous. The universe is created ex nihilo, nothing material that we know of. Nothing like anything you can see in this room, not even a vacuum. So no space.
So Phil, why aren't you worried? If you think things can begin to exist without causes, then why aren't you worried, as the common line of argumentation goes, that a deer has just spontaneously begun to exist in your kitchen and is currently destroying it? Shouldn't you go and check?
Well, I asked Vilenkin this. I sat in his office and I asked him, I said, why can't a tiger just appear in this room? And actually he said to me, well, a tiger could appear in this room. There's a quantum probability of that happening.
Yeah, that is true.
Right? But it's just unimaginably unlikely, so no need to worry about it.
But that wouldn't be out of nothing, right? That would be out of the...
No, that wouldn't be out of nothing.
So why aren't you worried that a tiger might pop into existence out of nothing? Not as a really unlikely quantum fluctuation of atoms or whatever, but out of just like nothing. There's no space, there's no nothing. It just a tiger just appears. Why aren't you worried that that's going to happen right now?
Well, we're not in nothing. So if it can come out of nothing, well, that's not where we are. We're in this universe. So it has to play by the rules of this universe. Now, the question is, could a tiger appear out of nothing, like not empty space, sorry, just space.
Nothing,
right? Well, what Vilenkin tried to do was to use inflation. Say, look, the probability of a universe coming out of nothing and actually lasting is incredibly small. But what he suggested, and this is why it's called tunneling from nothing, that it could tunnel to a state where it would then inflate and become a big universe. So if it was just a tiger with no inflating energy, then it would just sort of go back into nothingness, as it were.
Sure.
But so now let's go on to this issue of causality.
Yeah.
Right. So if the universe came from nothing, would it need a cause? Now, what I want to do is ask the question, well, let's suppose God created the universe. Does God need a cause? Right? And the reply is often, well, God doesn't need a cause because God doesn't have a beginning. It's
God
only
necessarily exists.
God doesn't have a beginning. It's only things that have a beginnings need causes.
Yeah, that's
right?
how the Kalam.
Okay, yeah. So that's in the Kalam argument. Now, that's not the statement that God exists eternally into the past, right? But rather the claim is that God exists timelessly and then enters into time. But now let's go back to Neo-Ayesh's holographic cosmology model. That also exists timelessly and then enters into time. And we might make an argument for the Hartle-Hawking model, which also has a timeless state. So here, maybe then we could say exactly the same thing, where it doesn't need a cause, right? So the question is like we said about water being emergent, causality may be emergent. So then when we get to the quantum realm, maybe causality doesn't exist. So causality is a feature of our macroscopic universe. So we can't assert that these things must have causes because we don't know if causality is fundamental.
Yeah, this is kind of like a version of when people say, well, the universe needs a cause and that cause must be God. There's some kind of first cause or some kind of necessary existence. And a very common response to this from atheists is to say, well, in some sense, the universe can serve that role, right? The universe is this brute fact. The universe necessarily exists. People come along and say, no, the universe doesn't necessarily exist. It had a beginning. How do we know that? Hilbert's Hotel, the Big Bang. We've gotten rid of those ideas, right? So let's say that we can no longer dismiss the idea that the universe is this fundamental thing, which sort of, from which everything else stems. And all of the qualities that exempt God, I think legitimately, by the way, philosophically, I don't think it's a cop-out to say, well, God doesn't need a cause. I think that's perfectly philosophically legitimate. What we're saying now is it might be equally legitimate to apply that to the universe or whatever sort of was the Big Bang or before the Big Bang. Here's the question, and this might be a question for you, Nayesh, because you've got this holographic view of time. And earlier, this is what I was trying to wrap my head around. Time doesn't exist, and then it does exist. Here's what the theists say, and here's what I say when I'm on my sort of theist day on. I say, okay, so we've got this timeless cause, but we've got a temporal effect. Right? The universe, which has popped into existence, it has time. It's got a temporal effect, but the cause is existing timelessly. In a sense, it sort of exists. You might want to say infinitely, maybe not eternally, but definitely timelessly. Here's the problem, right? If you've got a timeless cause that just exists timelessly forever, there's no beginning to it, it just exists.
You used to said forever, so that doesn't mean timeless.
Exists outside of time. There's no point in time at which it doesn't exist. Let's say that, right? If there's no point in time at which this cause doesn't exist, if that cause is causally sufficient to bring about an effect, imagine it's like it entails the effect. Imagine the cause entails the effect. If you've got a cause which has the ability to bring out an effect, and that cause exists, there's no point in time at which that cause doesn't exist, then since that cause brings about the effect, there should be no point at which that effect doesn't exist, because the cause brings about the effect, the cause is timeless, so the effect should be timeless too. In order to have a timeless cause that yet brings about an effect at a point in time, that cause needs to do something. It needs to have, in other words, as the theist would say, a will, or it needs to have some kind, it can't just be this inert law, because laws apply all the time, right? Laws don't sort of change and fluctuate. So you've got this no point in time at which the cause doesn't exist, there should be no point in time at which the effect doesn't exist. But if there is a point where the effect doesn't exist, but no point at which the cause doesn't exist, the cause must do something, must have some kind of will. We're looking at something that looks a bit more like God than some foundational law of the universe, right? You get what I'm saying?
Yeah, it seems to me that it's kind of getting more complicated than it should be. I mean, I guess that this timeless story, maybe it's, we miss stated it. I guess it's timeless in the sense that in this earlier state, there is no time. There's only a space. But you could also say that it exists at one time. So it's not that it exists all the time. So this initial state, this three-dimensional timeless state, it's not that it exists eternally. It just was there. That's a proper way of understanding the universe at early times. Now, here's the thing. It's not that there is one or the other, right? So I think you're kind of separating the cause from the effect. And I think maybe in a kind of roundabout way, I kind of agree with you, because this idea of holography is not that one is real or the other is not real. So the idea is that there are two different descriptions. Mm-hmm. Okay, there is one description with time, and there's another description without time, and they're equivalent description. There's not one, neither of them is higher or better or different from the other. They are the same descriptions. They're just easier to kind of put it in human language or mathematical language in some situations. One is easier in one situation, the other is easier in other situations. But nonetheless, they're equivalent. Okay. So in that sense, I think I agree with you that if you want to say one of these is the cause, the timeless one is the cause, and timeful one is the effect, then they're in fact the same things. So we are the God. Is that right?
Well, I really thought we'd get to the end of this without any kind of blasphemy. We just about managed to slip it in. Okay, that's interesting. And of course, like a model like this holographic universe is even if we spent the whole podcast talking about it, there's too much to go into, which is why once again I will wave the book around and implore people to go and buy it, because I mean Carlo Rovelli on the front cover describes this as an intellectual feast, and I think he is right. It is phenomenal. So many questions left unanswered. I mean, one is to say that, like, okay, so we were just talking about this, Phil. Recently, Joe Rogan went viral for saying that he's, quote, sticking with Jesus. Reason being that the difference between science and religion is that science only asks you to believe in one miracle, that the universe just sort of pops into existence out of nothing. Okay, maybe that relies on this idea that the universe has a beginning at a point in time, which, as we've discussed, it might not. The universe might be infinite. But as I said, even if the universe is past eternal, it still seems that there would be some reason why that eternal thing exists. And so Joe Rogan says that the miracle that the scientists ask you to believe in is that the universe just sort of exists for no reason or out of nothing, or however you want to think about it. And like, if you think it's so ridiculous to believe in the miracle of the resurrection, isn't it equally ridiculous to believe in that kind of miracle? And isn't science therefore ultimately based on a similar kind of faith?
Well, let's separate the two miracles, right? One is that the universe came from nothing. And I think we can say for sure that we don't know that to be true. It's not impossible. Valenkin has this interesting idea, but as we explored, there are lots of interesting ideas, and we have to embrace the uncertainty. I think that's kind of the theme of the book, is when people tell you, the universe came from nothing, or it had a beginning, or all kinds of ideas, embrace the uncertainty, because we don't know, right? So we can't say the universe came from nothing. So Joe Rogan, I think, is just misstating the case here. But that doesn't mean we shouldn't address this issue of what's the reason that the universe exists. So another interesting model that we haven't talked about too much is this idea of a time loop. And interestingly, this would also challenge our notions of cause and effect, right? Because what's the cause and what's an effect if we're on a loop in time? And William Lane Craig said that this was a desperate attempt by atheists to avoid God. But what he didn't know is that Richard Gott, who came up with this model, was actually a believer. So the question might still be, well, why does the universe exist? And I think what we can do in cosmology is not necessarily to answer these really big questions. I mean, that's for philosophers. And what cosmologists want to do is push the envelope of our knowledge. So we've got a point, the Big Bang, where our knowledge currently sort of stops. And what cosmologists want to do is push beyond it. And that's the battle. But I don't think that's going to give us answers to, why does the universe exist? I mean, you can try and make inferences about it. Like if we look at the Vilenkin tunneling from nothing model, you could say the universe exists because the laws of physics exist. And maybe the laws of physics are necessary. Maybe they just couldn't be anything other than what they are. So if you're looking for the necessary thing, maybe it's not God, maybe it's the laws of physics. And I kind of like that better than God, because we know the laws of physics exist in some sense. Now, exactly in what sense they exist, that's the thing for debate. But I like that better than God, because I think, laws of physics seem more parsimonious. But of course, this is a speculative idea. And maybe there is no reason. Maybe it just is. And, I think Bertrand Russell just said the universe just is, and that's it. So I don't think cosmology is going to settle those questions. But what it can do, what we hope it will do, is push the edge of our knowledge from just after the Big Bang to maybe
So
before.
Joe Rogan might have the wrong idea of what the Big Bang is and what you're required to believe to accept the Big Bang. But it's not illegitimate of him to go, but look, at least the kind of scientist that says, well, the Big Bang has, done away with our need for religion and sort of has explained everything. Actually, no. In order to think that the Big Bang has somehow explained the beginning of the universe, you kind of are believing in some kind of miracle, if at least the miracle of explanation, which scientists just cannot even begin to approximate right now. Is that putting it too strongly?
I don't know if I'd want to use the word miracle. There are certainly unanswered questions that I think physics, it's not setting its task to answer.
Do you think Joe Rogan is embodying an illegitimate criticism there as a whole, which is to say, okay, maybe he's got the wrong model of the Big Bang or whatever, but even if we corrected that and said, Rogan, maybe the universe didn't come from nothing, maybe it's past eternal, he goes oh, okay, that's interesting, but still there's this question of why it exists, and the scientist is just asking me to just accept that there is some reason that we just don't know, and it's I'm sticking with Jesus because that's more sensible to me.
Well, we asked you to embrace the uncertainty, and sticking with Jesus is not embracing the uncertainty.
So you're not asking someone like Joe Rogan to say, don't stick with Jesus, stick with, the quantum loop theory, because that's the correct. It's rather, don't stick with Jesus because we don't know what to stick to yet. Maybe it's Jesus.
Yeah.
And maybe if it is Jesus, science isn't the method we'll use to find that out. But the resistance to this religious impulse is not because you have a better explanation, but just because you have alternative explanations and we don't know which one is the correct one.
I think that's
fair enough.
Perfectly. Yeah.
Nayesh, do you have a view on this?
I think this is just a misunderstanding of kind of scientific method, saying that miracle, of course, is a loaded word. Depends on, I guess, if you're religious or not. Depends. You feel differently about it. But anything you asked this earlier, that okay, does the rules break? Do the rules break at the Big Bang, or do? And I was gonna say, and I can kind of say that again. 150 years ago, the rules of physics broke at the surface of the sun. So was God there?
And at some point the laws of physics broke near the speed of light. The laws of physics broke, with really, really heavy objects.
That's right, absolutely. I mean, at various stages in the development of science, we had certain rules or laws, approximate ones, and they were very good in some domains, and then we pushed them, at some point they broke down. And 150 years ago, that was the surface of the sun. And then we learned about relativity, learned about nuclear physics, and then we could then explain how plasmas behave, how convection works in plasmas, and how nuclear fusion works. Now that point is near this Big Bang singularity, or a hot Big Bang. Are we making progress? I think we are making progress. I think we're pushing further. But I mean, it's kind of an arbitrary point to say that, okay, so now this is where the science is going to end here, definitely. And it could have ended, I suppose, any point in the past 300 years, at any point, but it hasn't. It's been making progress steadily, and we're doing the same things. But I think about kind of broader implications of whether, is there room for religion in science? I think there is. I think this is more of an evolutionary question as opposed to maybe scientific. Still a scientific question, but maybe science of humans, not science of cosmology. Which is to say that, cosmologists are humans, and humans have lived with religions for for thousands of years, if not longer, as far as we know in written history. So the question, and this is the question I like to ask, that you can take a cosmologist out of religion, but can you take religion out of a cosmologist? I mean, if this is something that's built into our DNA, because okay, I'm not Christian, I'm not Muslim, I'm an atheist, but then you're still living life the same way your ancestors have been living. And I mean, on the surface it's very different, but we are still drinking water, we're still breathing air. So certain things in our brain may work the same way, and maybe we kind of develop religions in new senses, like, for example, is inflationary cosmology or a string theory modern day religions? And we kind of go into length as to what extent that question even meaningful, right? That maybe in some sense there are similarities, but then also there are differences. I mean, where we do make connections to experiments or nature, we pose testability or falsifiability as a criterion. Maybe that's where we try to distinguish ourselves. But I mean, this is a very fuzzy kind of a gray area, exactly where science becomes religion or vice versa. So it's but I think that's one thing that I think religion. As much as we may want to distance ourselves from ancient religions, I think this is part of our society, and it may show up in different guises, in terms of dogmas or in terms of the way we build communities. Like, I mean, religion has been used to build communities for thousands of years, and we build communities among scientists. Are we using similar practices?
Yeah,
right?
like science is not immune from dogma. This is the point. And in fact, we were just talking before we shot about how is it chapter 10 of the book that talks about like the relationship to religion and science, and you want to ask the question, like, as if I just asked to you, Phil, sort of, well, is there place for religion within, or is there space for cosmology within religion? You know, does cosmology sort of fit within this religious picture? The question you want to ask there, Nayesh, is, you know, is there space for like religion in cosmology?
Right.
At least those elements of religion which involve dogma and faith and belief without evidence, like that can occur in science too. And the history of science is littered with people who are unable to accept consequences of particular ideas because of essentially dogmatic assumptions. Famously, Einstein's blunder. I talk about that a lot on my show. Ironically, maybe he was right, you know, in a way he didn't realize. But the idea that, you know, his theory of general relativity showed that the universe had to be like, well, he believed that the universe was eternal and static. But general relativity said that it would all collapse. Right. And so he introduces this cosmological constant which holds it in place. And then when he realizes that the universe is actually like expanding and not, you know, static, he's like, I was so silly. He takes it out. He calls it his greatest blunder. And it was because of a philosophical commitment that he wasn't sort of willing to let go of. And philosophical commitments have gotten in the way of science, not just like religious institutions standing in front of scientists and saying, you know, you shall not enter, but scientists themselves unable to shake certain conceptions. And one of my favorite things that I've just thought about that you do in the book, when you're talking about the multiverse in particular, and this idea that the multiverse is ridiculous and like, it's so silly and speculative, and as if there are billions of multiverses. So like, come on, universes. And you very briefly, in like one sentence, track this history of science where you say, well, it used to be that the Earth was special and there were no other planets. Then we discovered actually there are other planets. But our sun is really special. We realize that the planets go around the sun, and our sun is this really special object, separate from all the stars. And then we looked at the stars more closely, and we realized actually there are billions of suns, and all those little stars are actually the same as our sun, and there's nothing special about it. And then we thought, okay, but like all of these stars are sort of collected into this galaxy, and there's this one galaxy that we all exist in. And then we started seeing these fuzzy objects in the sky, which Kant calls an island universe. And people are like, no, it's just some kind of weird star or something. And then, thanks to the work of the Harvard computers, some very, very like undersung heroes, women who were sort of doing the calculations that allowed us to discover, because of a particular kind of star in those fuzzy patches, that actually those fuzzy patches are galaxies as a whole. So first the Earth was special, then it wasn't. Then the sun was special, then it wasn't. Then our galaxy was special, then it wasn't. There were lots of galaxies. And now our universe is special. Where's this heading? You know, I don't want to extrapolate unfairly, but it seems at least plausible that one day we will look back in the same way as we look back on those instances of science. And people who are unwilling to accept that as a conclusion may just be beholden to philosophical ideas. Not to say that you have to accept it's true, but if you are just unwilling to entertain its plausibility because it's just ridiculous, think how many times that has been said about so many scientific ideas, to the extent that scientists have been like laughed out of the room. The first guy to like look at the continents and think, you know, it kind of looks like the Americas slot into like Africa and Europe, laughed out of the room, you know?
Right.
Yeah.
And yet we now know that to be the case. I think it's a good reminder. And I think reading a book like this, as I say, it's in part a history, going over the history of this happening over and over again is a reminder to be like, we just don't know, man.
Right.
We just have absolutely no idea. Maybe we will one day. But for now, at least, I think this is the best we've got. And I think this is one of the best overviews available in print. It probably is the best available. I should have said the best available. Honestly, guys, I told you this earlier. I think the book is a triumph. I think it's phenomenal. It's gripping. It's so well written. It doesn't have any bloody maths in it, which is awesome. And it covers all of this kind of stuff. We didn't even talk about whether you can create a universe in a lab. We didn't talk about quantum loop gravity. We didn't go into all the implications of causation and religion and stuff. I mean, how many chapters is it in total? 12 chapters. String theory, the big bounce. You know, we didn't talk about the big bounce and you know, timer-shaped universes and universes that are self-causing. It's all in here, and perhaps we'll have to do this again sometime to cover it even more, but I can only recommend that people go and read the book. It's out now, right? It's out now.
It is out now.
The link is in the description, so everyone go and check it out. But guys, thank you so much. It's been fun.
It's been an absolute pleasure, Alex. Thank you so much.
It was wonderful. Thank you very much, Alex.
Simon Blackburn, welcome to the show.
Thank you very much. Thank you for having me.
Most people who think about ethics know that there are kind of two ways of thinking about it. You've got realism on the one side. Ethics is a real thing. There are real truths to know about facts like murder is wrong. And anti-realism on the other side, that ethics is not real, that it's made up, a matter of opinion, that kind of thing.
Right.
Most people are familiar with that distinction, and maybe we can dig into it. But there's this other distinction which sometimes crops up between cognitivism and non-cognitivism in ethics, which is not the same thing. So could you tell us what cognitivism and non-cognitivism in ethics is?
Well, of course, the root for cognitivism is knowledge, cognition, and the battleground is, or used to be, between the realists who say we have knowledge. It's not only that there are real truths out there, it's also we know which they are. That's cognitivism. And non-cognitivists who said, no, it is made up. It's not a question of knowing anything. It's a question of liking things or approving of things or choosing things. And it's a matter of foisting our sentiments onto other people. So that is, as you rightly say, the battleground. Cognitivism then is not readily distinguishable from a generalized anti-realism.
Or non-cognitivism.
Non-cognitivism is not readily distinguishable from a generalized anti-realism, and cognitivism not readily distinguished from realism. In fact, I think the terms have been used quite interchangeably in the literature.
Interesting. So I was under the impression that to at least some degree, cognitivism was about truth value, in that if somebody thinks that ethics is cognitive, it means that it's the kind of thing that can be true or false.
Yes. And
the non-cognitivist thinks not. So when I think of, say, an ethical subjectivist or a moral relativist who says, well, murder is wrong, is true for me, but false for you, it's cognitive in that it's got truth value, but it's not realist.
Well, that kind of subjectivism is not a very popular option for reasons we could certainly come to. So it's not. I don't think the terminology has been tailored to take account of that. You are right there that cognitivism is always associated with the presence of a truth value.
Yeah.
That's why it's associated with realism. It doesn't really have to be, because if you think of knowledge, then there's knowledge of things that are true, certainly, but there's also knowing how to do things. And so people who are called non-cognitivists might allow themselves a piece of camouflage, saying, well, actually, I'm quite cool about cognition. It's just the cognitions I allow and pieces of knowing how to do something. After all, Socrates, starting the ethical debate all those years ago, tended to think that it's a question of knowing how to live. And that's why it was so important. So he didn't deny that there was knowledge in the area. It was just a question of knowing how rather than knowing that.
Sure. How much of our moral terminology do you think is useful and accurate? Like we talk about realism, anti-realism, and cognitivism, and non-cognitivism, and knowledge and stuff.
Yeah.
Is that sort of the state of the language? Is it suitable for you?
No. I mean, I've spent an awful lot of my career trying to dismantle the way those oppositions are framed and the arguments that are used against one side or another. Mm-hmm. And I think by now they've become very stale. There are still people who call themselves realists, but they're, as it were, a diminishing tribe. There are people who call themselves anti-realists, and they're probably a diminishing tribe as well. So, curiously, the battleground has started to occupy fewer philosophers than it did, say, 50 years ago when I started writing about it.
So what are people using now if they're not tending to call themselves realists and anti-realists? There are still people who believe there's truth in ethics and not truth in ethics. What kind of language is being used?
The language of truth, partly. Uh-huh. But that too has its failures for reasons we might come to. One of the most popular contemporary theories of truth is called deflationary theories of truth. Mm-hmm. And those permit talk about truth almost everywhere, that you've got an indicative sentence, like there are cameras in this room, or that's red, or you're wearing a jacket, and so on. So if you say those things, you can say that they're true. Or, of course, false, as you find them.
Okay, so let's dig into this then. So there is this idea that a lot of people want truth in ethics. When you say that murder is wrong, you want to be able to say that that's true in the sense that it's true that the Earth orbits the sun. And the great trouble with this is a lot of people say, well, in order for that to be true, there'd have to be this sort of weird element to our reality, that there is this property of wrongness, which Mackie famously describes as queer, as like totally unlike anything else. And if it does exist, it seems impossible to know how we'd even apprehend it. And yet we have this burning desire to say that there is real truth in ethics. I think you could probably call this the realist appearance, the appearance of realism intuitively for people.
Yes, I think you could. And I think it's seduced a lot of people. I think the rot started. This is very treacherous of me to say this because I was brought up in a college which was Moore's College in Cambridge, and Moore was still a very important figure to people in Cambridge, including especially my own supervisor. So I do feel very nervous about saying what I'm about to say, but I think the rot started with Moore.
Really?
In his 1903 book, Principia Ethica, Moore decided that there was a property of, well, he talked about goodness more than rightness, but for our purposes, we can take them as equal to the other. There was such a property. It belonged to some things, and it was a non-natural property. That is, it wasn't like the properties of things which fall within sense experience. So it required a special mode of knowing. And then you're off to the races because where are you? Because you've got a supernatural or non-natural property, and you've got a non-natural way of knowing about it. And that, known as intuitionism, it was christened intuition.
Yes.
Sort of set the scene for 20th century discussion of these things. I think it led people up a garden path. If you look at great classics of ethics, for example, the Scottish sentimental tradition, Hume, Adam Smith, but even as late as John Stuart Mill, Bradley's doubtful, but most of those people, certainly the ones I mentioned, didn't trouble their pretty heads about non-natural properties and the fugitive nature of ethical knowledge. They either were unabashed sentimentalists, like the Scotsman, like Hume, Shaftesbury, English, but then Hume, Robertson, Hume, and no, not Robertson, I shouldn't have mentioned him, but Shaftesbury, Hume, and Smith, Adam Smith. And you can read, say, Hume and Smith without ever finding worries about subjectivism, worries about naturalism, worried about non-naturalism. They just go ahead and tell you how ethics works. And this I admire them for, and I think they were on the right track.
Yeah.
And I think we were deluded by More into thinking there was another question, the question of the nature of the moral property.
Might be called like moral ontology.
Exactly.
It's interesting. You know, I've spoken to a few physicists on the show recently, and we've been talking about functionalism as a view of what science does. So there's this great debate as to whether science really explains anything about the nature of the world or whether it just tells us what stuff does.
Yes.
So famously, Newton describes gravity,
yes,
discovers all of its laws, but has no idea what gravity actually is. And I suppose there's an extent to which I'm thinking now that could be mirrored in ethics. You know, are we, when we do ethics, just talking about what ethics does and what people do when they make moral claims? Or are we talking about what the good is? And it sounds like you're more in line with the former idea.
Oh, I'm very much on board with the former idea. If we look back in history, let's look at David Hume, writing in the middle, roughly, of the 18th century. He says an awful lot about what counts as a virtue. He's a virtue theorist. He puts virtue front and center of his discussion of ethics. He tells you about the properties that are involved, qualities of mind useful or agreeable to yourself or others. Or actually, there's an and there, qualities of mind useful and agreeable to yourself and others. So that's the properties we're talking about. What do they do? Well, they excite admiration in us.
Right.
What do we then do? We express that admiration. And that's it.
But there's no question of what is
not
a
beyond,
virtue.
Not beyond saying
what it does.
What the qualities are that excite us.
That's really interesting, because when I've spoken to physicists about this in the scientific context, I sort of am a bit dismayed. I'm like, but you know, you're not telling me what an atom or a subatomic particle actually is. You're just telling me what it does. It's negatively charged, whatever. And they sort of look at me and say, but that's it. That's what explanation is in science. And maybe the same thing's true in ethics.
Well, I think it's true, yes.
Yeah.
I think Hume was absolutely right to stop where he did. That is, there should be no final question about the nature of the ethical property, the property of rightness, the property of goodness. That's a metaphysical question. We don't have to go there. All we have to do is to say what excites us, how we react to it, and the way we express that reaction.
Does this approach rule out the idea that there is this property called goodness that has a nature, or does it just remain agnostic on that question?
That's a very good question. I think it invites you not to ask it,
right,
and not to expect an answer of it. As you're finding talking to your physicists, they're not ready to give an answer.
Yeah.
Of course, there have been people, I think Immanuel Kant was one, who thought that shows that we're confined to the world of phenomena. That is, we've got the phenomena of physics. But but we can't really find out what are the properties of things in themselves. And that's so what you're voicing, or what people who dislike the physicists' functionalism are voicing, is basically sympathy with Kant, that there is an extra potential object of knowledge, the things in themselves.
Yes.
Now, you get exactly the same when Hume talks about causation. That was arguably his other great contribution to metaphysics. There's the properties that set us off, and these are just regular successions in nature. We find that when one thing happens, another happens. When we've got a regularity like that, and we're confident of it, that makes us expect the second on the occurrence of the first. That expectation is very it's irremovable. It's not something we've got control over. And so we express that by saying the second must happen. We use the modal language. It must happen if the first happens. If you ask, where's the must? Do we see the must?
Yeah, where is this causal connection?
No, we don't.
And Hume wonderfully sort of looks, he takes the magnifying glass to, you knock one billiard ball into the other billiard ball, and one causes the other to roll, and he's like, well, I can't see this causal connection. I can't see it in the first ball anywhere. I can't see it in the second ball. It's not floating around in the air somewhere. So where is it? And he sort of says, well, I don't really know. And so it restricts our ability to meaningfully talk to what's happening. And the reason I think that's so exciting is because in the scientific context, people are quite willing, I find, in talking to them, to sort of say, yeah, okay, fair enough, we can't really get at what stuff like fundamentally is, but that's enough. Like, science is a good enough enterprise just telling us what things do. But when it comes to ethics, they demand something more.
Well, I'm sorry for them, because I think they won't find anything more.
Right.
As I say, if they go down the rabbit hole that Moore opened up, they'll just find themselves in darkness. There is nobody's ever said anything intelligent about it in how we intuit non-natural properties.
Yeah. Well, I kind of think that another good word for intuition might be feeling.
Well, now you're on Hume's side.
Yeah.
Because if it's a question of how we feel about things, Hume's your man.
Yeah.
Or Adam Smith, who's actually a wonderful psychologist.
Yeah.
So, this is you coming down on the side of what were traditionally known as anti-realists. A lot of my own works, which go under the title of quasi-realism, which I now regret, but I'm responsible for it. That was endeavoring to show that the feeling side, the sentimental view, the Scottish sentimentalism, wasn't as bad as people thought. I think there was a reaction against it, partly probably due to the Second World War. After people discovered the full horror of the Nazi atrocities, they weren't content with existentialism, with the view that you sort of make it up for yourself, or you mold yourself as you choose. They wanted constraints. They wanted to be able to thump the table and say the Nazis were really bad, and if you don't believe that, you're wrong. And my endeavor was to show that the expressivists, or people on the sentiment side, could say that. That is, that these certainties, as it were, shouldn't be the private property of realists. In fact, if anything, I think the boot's on the other foot. It's easier to explain the certainties in an expressivist or sentimental tradition than it is if you're a realist. After all, if you're Moore, how do you know you're entitled to thump the table about how bad the Nazis are? By intuiting something? It didn't take intuition for the people who went into Belsen and Auschwitz to understand that something terrible had happened there. They didn't need to intuit that there was badness in the air. They just needed to feel revulsion, and feel ashamed almost to belong to the same species as the people who did this. And it was that kind of revulsion, indignation, shame, which got voiced in all the table thumping. And good for them. I'm on their side. I think those were the appropriate sentiments to have in the light of those horrors.
Well, this quasi-realism, which you're famous for, I'm interested in why you regret the term, and maybe we can talk about that.
Yes.
But my understanding is you're sort of taking this non-cognitive understanding of ethics, that when people make ethical statements, they're essentially expressing something that probably doesn't have truth value. It might be something like an emotion or a command or a plan, but that in saying so, they're somehow projecting onto the world a realist language.
Yes, well, I used to call myself a projectivist, but the metaphor of projection is very dangerous.
Okay.
Because it does have a connotation of, as it were, illusion, or something which isn't quite as it appears to be. And I wanted to get rid of that.
Well, that's what it will sound like to somebody who, for the first time, comes across this idea that, oh yeah, ethics is just an expression of emotion. But I'm not an anti-realist. I'm a quasi-realist, because although I think it's all just expressions of say, emotion, to take one example, there's something somehow real about the way I'm talking about it. Like, how is that different from?
No, I mean
from that.
The way I thought of it was that the realists, or people in the realist camp, felt that they could say things which the anti-realists couldn't.
Right.
So they could talk of truth and fact and reality and so on. I want to say, well, wait a second. What does that talk add to just saying that the Nazis were dreadful? And I was abetted in this by a book that came out in 1990 by a man called Paul Horwich, very good philosopher in Cambridge, just on truth. And Paul championed the deflationist view, which I mentioned earlier. Now, of course, if you've got a deflationary theory of truth, there's no difference between saying the Nazis were bad and it's true that the Nazis were bad. Same thing. It's really true that the Nazis were bad. Same thing. It's really true that it's a fact that the Nazis were bad.
It's true that it's true that the Nazis were bad. Yeah.
So, in one of my works, I call that Ramsey's Ladder, after Frank Ramsey. And my use of the metaphor was to say that the Ramsey's Ladder is lying on the ground. It's horizontal. It doesn't carry you any higher or anywhere different.
That's brilliant. Talking about this regression of it's true that, because people, for people listening, it might be helpful to think about this in terms of truth in the popular imagination, at least for a long time. And I think probably amongst most normal people, as it were, today, what does it mean to say something is true? Well, it means that what I'm saying somehow accords with reality, the so-called correspondence theory of truth, right? When I say the chair is red, there is a fact about reality. There is this chair, and it has this property of redness, and the words that I'm saying correspond to the truth of that real thing in the real world. And so to say that something's true is to say that it corresponds with reality. The deflationary theory of truth doesn't so much offer an account of what it means to say something is true as to just say that it's just adding nothing. Like you just said, the difference between the chair is red and the chair is red is true doesn't exist.
Doesn't exist.
For the correspondence theory, there is a difference there, because to say the chair is red is just to express that as a view. To say that the chair is red is true is to say that that statement corresponds with reality. But for the deflationist, it's just to sort of express the same thing twice in a row, basically.
Yeah, that's right. Now, there's a utility to the word true, which we can go into, but it's a very different utility than anything that the correspondence theorist gets hold of.
Yeah.
I think the thing to say about correspondence is it's perfectly harmless. Of course, it's okay to say that if something's true, it corresponds with facts.
Mm-hmm.
That's because facts are made for that role. Fact is something we invent for a true sentence to correspond to, or true proposition. The mistake is to think of the facts as something separate and apart from the beliefs that we hold, and the beliefs we cling to, and the beliefs that have stood the test of time, and which we therefore want to express and want other people to believe. The epistemology is not one of, now I've got a belief, let's say I believe that you're wearing a jacket. Now let me see what the fact is. Oh yes, the fact is that you're wearing a jacket. That second process wasn't different from the first process. All I was doing was reassuring myself, perhaps, that you're wearing a jacket, which is sometimes a perfectly good thing to do, because you do need reassuring. If you think, but you think are not very certain that there are eggs in the fridge, then of course you reassure yourself by going and looking. And going and looking is certainly a process which puts you in a better position to assert that there are eggs in the fridge.
Yeah. And it's helpful to think in terms of these partial beliefs. Like you might say, I'm not sure if there are eggs in the fridge, and therefore you would say, I'm not sure if it's true that there are eggs in the fridge.
That's right.
That makes sense for the deflationist. But if you really can separate, this idea of the statement of the fact there are eggs in the fridge to the truth of it, then I should be able to say something like, there are eggs in the fridge, but I don't know if it's true that there are eggs in the fridge.
Yes, and that's very awkward.
Doesn't make very much sense. And this ladder that you were referring to also, if I'm not mistaking you, would refer to the fact that for the correspondence theory of truth, to say something is true means there's a reality it accords with. Okay, so this chair exists. That's the reality.
Yeah.
And so I can say it's true that the chair is red, because that accords with reality. Well, I've just created a new fact.
Yes, that's right.
And that new fact is, it's true that the chair is red.
Allegedly, yes.
So I can now say, well, it's true that the chair is red. And that creates a new fact.
Yes.
I can say it's true that the chair is red.
Right.
And that can go on forever.
Yeah, and yet there aren't that many facts.
Yeah, exactly. And so when you think of it in those terms, when I start saying to somebody, but that means it's true that it's true that it's true, and that means it's true that it's true, that they would probably stop me and say, you're not adding anything.
That's right.
Every time you say that it's true.
That's the idea behind the metaphor of the ladder's line.
That's this ladder that goes sideways.
It's not going any higher. The first philosopher to use that argument you've just used, which is a very powerful argument, was Frege.
Yes,
And an argument that's good enough for Frege and Ramsey and Wittgenstein and Strawson and Quine is good enough for me.
Oh, yeah. And I think this might also have some interesting implications for believers in God, because of course God is omniscient, which means he knows all true facts.
Yes.
And if you have this problem of regress, that every time you say something is true, you create a new fact, and that sort of gives you this infinite regress, that would mean that God needs to know an actually infinite number of things, which almost seems a bit redundant. Like most of God's cognition is taken up and it's true that it's true that it's true that it's true.
Yes.
And so maybe this isn't a good way to think about truth.
Well, exactly.
And if it doesn't add anything to say it's true that, like for the 15th time, maybe it also doesn't add anything to say it for the first time. Indeed. And so we have this idea of deflationary theories of truth, that to say the chair is red is true is just to say the chair is red. And one of the reasons this is so popular amongst non-cognitivist ethicists is because in the moral environment, what the realist says, to criticize someone like me, for example, they'll come along and they'll say, well, Alex, I know you think that murder is wrong, but can you say that it's true? So I just did.
Yeah.
I already did say that it's true.
Yeah.
It doesn't add anything to say that it's true. And so it fits in quite nicely with an expressivist
You've got
ethics.
it exactly. You've got it exactly. That's right. And from about 1990 onwards, I mentioned Paul Horwitz wrote then, that's become gradually much more accepted, which is why I think the old labels of cognitivist, non-cognitivist, and so on are less popular today than they used to be. Those battle lines are not quite as solid as people used to think.
Yeah. For a long time now on this show, I've been telling people that, broadly speaking, I'm an ethical emotivist. I never like to commit myself to it just because I'm agnostic about most things, as I like to say. But I do try to make sense of what's going on when I see somebody kick a homeless person, and I feel something more than just the descriptive fact that a person's been kicked. What's this extra thing that I'm aware of in my mind? It seems like it's a feeling. It's something like stop or don't or boo or something like that, right? And so I think, okay, it might make sense to say that the ethical component of these statements is an expression of emotion. You yourself are not an emotivist.
Well, emotion, if you study emotion, you start to get very tied up with things like anger and fear, things which have a very pronounced phenomenology.
Yeah.
Your skin breaks into a sweat and this sort of thing. And that's what people associate with the idea of emotion.
Yeah.
I prefer to work with the term attitude. I think it has the same, it's got the same force, and it's got the same seat in our sentiments. But an attitude can be, it doesn't necessarily make you hot under the collar. I mean, I've got the attitude that Donald Trump's, no, I won't take that because that does make me hot under the collar. But suppose I have the attitude that it was a pity that Cromwell won the Civil War.
Right.
I regret that. I think it's such a shame. That doesn't make me hot under the collar. It's a perfectly, as it were, inert attitude. It doesn't by itself give me much of a motive to do anything. It would give me a motive to dissent from somebody who thought that Cromwell was a thoroughly good thing. But that's about all, because it's not part of my practical life. But emotions, I think, are essentially episodes in your practical life. And so that's why I don't entirely recommend the term emotivist.
Yeah.
But of course, there's no term attitudinalist, which is a pity.
Yeah. Well, perhaps we can start a trend. If people are watching,
would love to.
Let's get that. Let's get that going.
Yeah.
I don't know though, because I think that's interesting what you're saying, that you can have attitudes towards something, ethically speaking, without, as you say, getting hot under the collar. But even the way you just said then, because it's such a shame that didn't happen. I feel like maybe you have to pick something which, in order to find something which isn't that emotionally moving, you also have to pick something which you wouldn't actually find that morally important, like genuinely as something you would express.
Yes, I mean, it's unusual. It's not that unusual. I mean, consider people talking about fiction.
Yeah.
We talk, was Emma just a silly little girl, or was she a heroine? And you can imagine a couple of literary critics getting the pros and cons of that, bringing it up, knowing the text, knowing the episodes, what Jane Austen told us, what she didn't tell us, and so on. And they do it far better than I can do it off the top of my head. But it's not going to be something I mean, in any profession, as it were, if they're professionally arguing it, they can probably get hot under the collar.
Mm-hmm.
But in itself, it's not being hot under the collar about Emma's behavior. It's been hot under the collar about what's said about Emma's behavior.
Yeah.
And that's a different object of criticism.
Mm-hmm.
I think there are obviously history and fiction are two cases where you don't have episodes of emotion in the same way that you do if you, as it were, walked into Auschwitz. Then you'd feel the horror. But nevertheless, it's the case where you walk into Auschwitz which gives you your moral basis, your moral bearings. That's where you start, I think.
Do you think it would be possible in principle? This is just a question about motivation and ethics, I suppose. Would it be possible in principle for somebody to walk into Auschwitz, feel absolutely nothing, like nothing about their emotional disposition changes, and yet they truthfully express, this is wrong?
I don't think so, no. I think that they might mouth the sentence, it's wrong, but if they feel nothing, I think they're misusing it. I think they're not expressing a feeling that they've got. They're not expressing revulsion or a sense of shame or sense of horror, any of the things which you'd expect. And I think insofar as they're absolutely cold, then they may be mimicking moral disapproval, perhaps to show that they're part of the gang or something, but they're mimicking it.
We said that it's difficult to define what like wrongness is. We just talk about like what it does. When somebody looks at Auschwitz and they say that's wrong, and I'm not talking about someone who's steeped in ethical literature here, someone you meet on the street. I say, what do you mean by that? And they'd probably say, well, I struggle to define this thing, wrongness or badness, but they still mean that like there is this thing about something like Auschwitz that is wrong, and that's true. And if I try to offer an account of saying, well, I think you're essentially just expressing an attitude there, they would say, no, it's more than that. Like I'm saying something true about this thing called wrongness. Like at the very least, if we can't define wrong or bad in terms of what it is, can we at least get to grips with what people think they mean by those terms?
Could I pick you up on something? You did this before as well. When you talk about expressing an attitude, you tend to insert the word just, or just expressing an attitude, or you're merely expressing an attitude. And I think that has to be resisted. I mean, attitudes are extremely important.
Yeah.
It's far more important to me if your attitude towards me is that I ought to be shot, than it is if your attitude towards me is the belief that, I was at university in Oxford, which I wasn't. I was at university in Cambridge. You've got that wrong, but it's unimportant. Whereas if you think that I ought to be shot, that's not a mere attitude. It's, potentially a very dangerous attitude.
But some people will say that they're different kinds of statements, like the idea that, you studied at Oxford is not an attitude. It's a
belief.
It's a belief. It's a truth claim that's false. And I think that the person I'm embodying here would say that in the same way, when I say that, the Nazis were wrong, I'm making a truth claim. I'm stating a belief. This is something that I believe to be true about the world. And yet here we are saying that, what will sound to them as like it's just an expression. But
I think that the contrast between attitude and belief is not straightforward.
Me too.
So I think that we're apt to go down another rabbit hole there. We've already established that if you use the indicative form, you can use it. It's true that without blushing. I think it's important to put on top of that, and this is this takes us on to the notorious Frege-Geach problem.
Yes, thank goodness.
That the difference between expressing an attitude by means of an indicative sentence and expressing it in some other way is not cast iron. Language is very flexible at this point. So, to take a favorite example of mine, Cato allegedly said that Carthage was to be destroyed. Carthage delendum est. And Latin has the gerundive there. Now, he could just have said, let's go and destroy Carthage. That would have been an imperative form, but expressing an attitude of, dislike of the existence of Carthage, wishing to abolish it. He could have expressed his wish that way, or he could have said Carthage is to be destroyed. I think the second has a slightly more public face. It makes it plain that Cato doesn't think that he's out of line or idiosyncratic about this. He thinks that, all right-thinking people are going to agree with me, or I'm going to try and get them to agree with me. Carthage is to be destroyed. But the difference then, is a difference that Peter Geach did emphasize. If you just say, boo to Carthage, or boo to the existence of Carthage, let's do away with Carthage, you can't say if let's do away with Carthage, then one thing or another.
Mm-hmm.
If you say Carthage is to be destroyed, you can say
if
Carthage is to be destroyed, then is Tyre and Sidon to be destroyed with it.
Yeah.
Or if Carthage is to be destroyed, we'll need a bigger navy than we've got at present.
Interesting.
So on.
That's a great example, yeah.
So the advantage of giving the attitude, or the injunction in this case, the plan, an indicative form, is that it renders inference and discussion possible.
Mm-hmm.
Now, Geach famously said, this is an abyss that nothing can cross. Either it's on the side of boo hooray, it can't enter into these inferences, or it's on the other side, it's proposition, and then it can. But never the twain shall meet. And that's emotivism's problem.
Yes.
And a lot of ink's been spilt about this. This has impressed philosophers and worried them. I tend to nowadays to reverse it, to say, no, the exact reason that we have these interchanging forms is that when we use the indicative form, we know about making inferences. And we need to make inferences. The commander of the army needs to say things like, if Carthage is to be destroyed, then we're going to need a lot more ships. If Carthage is to be destroyed, we can't do it with the army we've got. We're going to have to employ some Spaniards, and so on. So anybody intent on serious planning is going to have to take the fruition of a plan as something he can make hypotheses about.
And he can embed
into these conditions.
Other statements, yeah.
But there's a reason for that. And the reason is the one I mentioned there, namely that it enables inference.
Mm-hmm.
And inference is important. If you just go around saying boo to Carthage, you haven't yet, as it were, given the commander-in-chief his marching orders.
Yes. You've just expressed a feeling or an attitude.
Yes, exactly. So it may be right to say that in ethics, or in some of the forms in which ethics takes, we go beyond just expressing feeling and attitude. You see, I use the word just there, just expressing feeling and attitude. I think and this was first pointed out by man called Charles Stevenson in the 1940s in the book Ethics and Language, we offer ethical discourse to each other, partly as a matter of persuading people, not just we're not just content to say, this is how it is for me. We're also saying, this is how I want it to be for you. I want you to share this attitude. So it's a persuasive exercise as much as anything else, or a reassuring exercise if I think you do share it, but I'd like to just hear that you share it. But having thought of it as shared, we then can also switch to the gerundive and think of it as something to be done. So there's something to be done. Carthage is to be destroyed. Let's build the army. Let's build the navy.
Yeah. I mean, you can't make inferences from expressions of emotion, like logically speaking.
No.
You can't say, if boo Carthage, then open a window.
No, that's right.
That just isn't, it's like saying, if 3, then go and open a window. It just doesn't make sense.
Grammatically not sensible.
And so, as far as I understand it, the so-called Frege-Geach problem, named after Frege and Geach, also known as the embedding problem,
yes, indeed,
is a problem for, I'll use the term emotivism because, with the caveat that we've said it might describe attitudes. Emotivism basically says that when I say murder is wrong, I'm just expressing an emotion about murder. Yeah, that's what I'm doing. And to be clear, one confusion, I'm not reporting what I feel.
No.
Like, murder is wrong doesn't mean I don't like murder.
It's not made true by your like or dislike.
Yeah, because it could be true that I don't like murder. That's not an expression. That's a fact about my brain. Instead, murder is wrong is the expression of that dislike. So it's, as Aya famously had it, something like boo murder, right?
Like
or
boo
murder and then an angry emoji next to it, right? With a bunch of exclamation marks. Okay, that's what is wrong adds. Okay, so it's just an expression. The embedding problem is about what happens when we use those phrases embedded in other contexts. So if I say something like, I wonder if murder is wrong, those words, murder is wrong, can't mean I'm expressing boo murder. Because I'm saying, well, I wonder if murder is wrong. But I can't say, I wonder if boo murder, if in order to say boo murder, I have to express something.
No.
And so you have this so-called embedding problem that either the emotivist is right, that this is what ethical statements mean, but as soon as they show up in, if-then statements, or, I wonder if suddenly it changes, or that's not what was meant all along. And what I want to focus in on here, because I want to take this somewhere, is specifically the context of syllogisms. So a syllogism, for our listeners, is an argument that has two premises and a conclusion. All men are mortal, Socrates is a man, therefore Socrates is mortal, for example. Now, here's one syllogism. If murder is wrong, then murdering Simon is wrong. Premise 2, murder is wrong. Conclusion, therefore, murdering Simon is wrong. That seems valid.
Absolutely.
And everybody will look at that and go, that the conclusion follows from those premises. The problem is, for an argument to be valid, means that the conclusion can't be false if the premises are true. But if premise 2, murder is wrong, is just an expression of emotion, I'm just going boo murder, then it can't be true. It can't be false. It can't be true. Any more than saying stand up can be true or false.
It's an expression of emotion in the indicative form.
Yeah. So in this particular context, to help us understand what this means, most people think of logical validity as requiring true and false statements, with true statements following from true statements. And yet the emotivist says that premise 2 there is an expression of emotion.
Yeah.
Which most people think expressions don't have truth value. So how do you get a logically valid syllogism from non-truth apt sentences?
Well, that's a beautiful exposition of exactly Geach's problem. He took the example, if lying is wrong, then getting your little brother to lie for you is wrong.
Yeah.
lying is wrong, so getting your little brother to lie for you is wrong.
Yeah.
It's exactly the same problem. Yes, well, it means there's got to be a complication.
Yes.
Now, the complication that I think does the job is the transition to the indicative form. Because we've already established, I think, as we talked about deflationism, that truth isn't going to be the problem. It's just if you've got the indicative form, you've got the possibility of inference. And my counter-geach is to say we've got the indicative form because it gives us the possibility of inference. Now, of course, you can give a functional account of why you want inference when you're expressing your attitude. I mean, one example was if you approve of giving money to the homeless, then you approve of giving money to female homeless. You need to be, as it were, able to be taken into account for your attitudes. If your attitudes are all in pieces, so you think that lying is wrong, if lying is wrong, then getting your little brother to lie for you is wrong. So, and then you don't say, no, but getting your little brother to lie for you isn't wrong. Well, you may be about to do a modus tollens, saying since not the conclusion, not the premises, not one of the premises. But otherwise, if you try and hold everything there, you're going to be in contradiction.
But can you have a contradiction if there's no... do you mean to say that when we put these ethical expressions into their indicative form, they do now have truth value? They are now the kind of thing that can be true or false?
Yeah, absolutely.
And that's because truth and falsity kind of is just an expression.
Yeah,
because to say it's true is just to express it.
Yes.
In that case, then, when I look at a statement like, if murder is wrong, then murdering Simon is wrong, I might say, okay, so maybe when I say that that's a true conditional, that's just an expression of the same thing, but what is the thing that I'm expressing in a conditional? Because I'm not, when I say if murder is wrong, then murdering Simon is wrong, if I say that conditional is true, I'm not expressing either of those component parts. I could think murder is fine, but I could say if murder's wrong, then murdering Simon's wrong, but I think murder's fine. So what am I expressing when I say that the conditional claim is true?
Well, there are various ways of putting it. I mean, one thing, this is going to sound more complicated than it is, would be you're expressing disapproval of holding the one attitude without holding the other.
Right.
So you're actually amongst your objects of concern is the lattice of implications in your approvals and disapprovals. Because approvals and disapprovals don't stand by themselves. We feel the need to defend them, feel the need to say what they involved. Supposing, if Keir Starmer says, I approve of, industry or something, you might say, do you approve of all industry? If you approve industry, do you approve of unpaid housework? And so on. We want to know what the implications of his approval are. Similarly for ourselves, we may not have realized that our attitudes carry an implication which we may not be all that happy with.
Yeah.
And teasing that out is part of the stuff and substance of ethical debate.
Yeah.
I mean, take, for example, the, what do they call themselves? Resolute kind of benevolent people who think you ought to give away all your surplus income above whatever the minimum that you settle on is. Have they worked it out? Well, if you do that, if everyone does that, then what will the consequences be for consumption and therefore for production and therefore for wages and the economy in general? I mean, if everybody does that, are you sure that the world as you know it will go on the same as you always expected it to?
Mm-hmm.
Be very nice for people who get richer, but it may be very nasty for everyone else. And it may in turn become very nasty for the people you thought you were helping. So unless you've sorted all that out, it's not a very sensible policy to go around advocating. Similarly, just stop oil. Have you any idea about the number of things oil is used in?
You
know, would you any longer be able to buy your fruit drinks in the cartons that you're used to? Would you any more be able to wear your fleece? Would you any more be able to wear your trainers? The answer to all those questions is no. But seeing that implication is something which I think you've got a duty to do.
Yeah, it's really important to be able to talk about the implications of ethical claims. But the problem for the emotivist is that if it's just an expression, it seems tricky to get these logical corollaries of ethical expressions. But the strategy I really like, and a strategy that that sent me down a path of all kinds of thinking when I first read it, was this particular strategy you just referred to. In response to the Frege-Geach problem, let's take that conditional statement, which I just asked you about. If murder is wrong, then murdering Simon is wrong. And we want to say that conditional is true without expressing either of those individual components.
Yes, that's right.
And you said, well, okay, what you're expressing there is a disapproval of holding one of those beliefs without the other.
Yeah.
And there's this wonderful sort of language you can construct around this. So if we adopt the boo, yay language of Aya, murder is wrong means boo murder. And murdering Simon is wrong means boo murdering Simon.
Yeah.
So how can we make sense of if boo Simon, then if boo murder, then boo murdering Simon? Because that's not just like true. You don't necessarily hold with those both.
Well, suppose, I mean, let's just say for simplicity's sake that the opposite of boo is hooray.
Yep.
So hooray would cover just tolerating something. It doesn't mean you actively approve of it, but you don't disapprove of it. Boo, boo to boo Simon without, boo to boo murder without boo murder Simon. You could put that in a parenthesis at a bracket. Booing murder without booing murdering Simon. That seems really weird. I can't get on all fours with somebody who says that. It seems, as it were, illogical in the strictest sense. Okay, so boo to that.
Boo to that whole thing.
thing.
So we end up with something like boo, brackets, boo murder at the same time as yay murdering Simon.
Yeah.
Boo to all of that at the same time. And that's what we mean when we say, if murder is wrong, then murdering Simon is wrong, because what we're saying is boo to boo murder and yet yay murdering Simon.
Yes, exactly.
So, and you have to do it in this annoyingly negative way.
Yes, and that itself gives us a motive for going over to the form we're all familiar with, the indicative form.
So let's take a look at this syllogism that we've got, which is, if murder is wrong, then murdering Simon is wrong. Murder is wrong. Conclusion, therefore, murdering Simon is wrong. So the emotivist says something like, premise 1, boo towards, brackets. So we're booing, brackets, boo murder and yay murdering Simon. Right? Premise 2 is, boo murder. And because we've previously expressed boo towards boo murdering Simon and
not
towards boo murder and hurrah murdering Simon, if we do express boo murder, then we've kind of committed ourselves to boo murdering Simon.
That's right.
And that's what the conclusion is. It's like this emotional corollary of expressing your discontent with these two simultaneous things and saying one of those things and therefore having to say the second thing.
Yeah, I developed a logic like that a long, long time ago. This was in Spreading the Word.
That's right, yeah.
And it's got its wrinkles. I mean, I still think it was very important to do it, because it showed that we're not, as it were, founding things on sand.
Yeah.
It showed that we need our attitudes to have the kind of structure and the kind of integrity as a whole that we also want for our beliefs. And that was, I thought, an important step in answering Geach, Frege Geach. It attracted a lot of discussion, some of it rather silly, some of it not. The most acute critic was probably a man called Bob Hale, who worked at St. Andrews, and he was a logician. And he had some quite interesting things about the recursions involved, about the increases in complexity. I think now I've sort of lost interest in the actual complexities of the 1984 construction. I haven't defended those in recent years, because I think the nerve of my current answer to Geach is that it's precisely because we want the inferential simplicity that we're used to in syllogistic reasoning, that we transfer to the indicative form.
Can I ask you then, and I know, as you say, this is a language that was concocted a while ago, and it might not best represent how you think about things now, but the thought that this caused to arise in me, let's say, is that I thought, wow, this is a really interesting way to emotivize if-then statements, right? Because I've got this problem that I think morals are emotive, but what about if it's a conditional? Oh, well, I can just emotivize the conditional. There we go, problem solved. Then I suddenly thought, well, couldn't we also then, in principle, emotivize all conditionals? So outside of just the moral, like boo murder and yay murder, let's take a non-moral claim, like if it's raining outside, then I'll get wet. Could I not also sort of say that what I'm doing there, if a deflationary theory of truth is correct, and by saying something is true, I'm just sort of expressing it, in some sense what I'm saying is boo, brackets, yay, it will rain, at the same time as boo, I will get wet. And so I've sort of emotivized non-moral syllogisms as well.
Well, I wouldn't use the term emotivize, but the same kind of theory was given for conditionals. In fact, it's implicit in Hume. If we go back to Hume on causation, he's going to give the same sort of story about if billiard ball A hits billiard ball B must go. He's going to give the same story about the if-then. You're daft if you think that billiard ball A hits billiard ball B without also expecting billiard ball B to go. But Gilbert Ryle wrote a famous paper, If So Because, back in about 1950. And he said that by issuing an implication, you're issuing an inference ticket. That is, you're permitting or allowing or maybe insisting. I mean, somebody who gives you a ticket doesn't usually insist that you go to the concert, but it may be that if you issue the inference ticket, you're entitled to go from A to B. If A, then B. It's also, as it were, an injunction that you've got to go from A to B, that you're at fault if you don't. So he talked about inference tickets, the licensing of inference tickets. Well, of course, licensing something is like expressing an attitude. It's not in itself saying something.
Yeah.
but it becomes saying something if saying something is the way to issue the license.
Yeah.
Which was exactly how Raoul thought of it.
Interesting. Because for me, I've hinted at this a few times, and careful listeners to the show might have picked up on it. I'm really interested in the extent to which the way the emotivist looks at ethics and says, I know you think you're being all propositional and truth claims and correspondence, but actually you're just expressing emotions. I wonder the extent to which we can apply that same thinking outside of ethics. So we've just done something like that to conditionals.
Right.
But like, the emotivist wants to say that just even the statement, murder is wrong, is some kind of expression or attitude. And I'm interested to the extent that we might be able to apply that to statements like, the table is brown, or you are wearing a jacket. And I don't know if that's something that, I don't know how much that has been explored in this context before, and where, I could begin to look to find interesting thinking on that.
I think you could find it probably at its most richest. I mentioned Ryle. Ryle, unfortunately, I think, worked in the 1950s in Oxford. And, of course, ordinary language was the sort of be-all and end-all under J.L. Austin. But Ryle had some roots in the pragmatist tradition. That is, the Americans, Peirce and James, and perhaps to some extent Dewey. And the pragmatists, rather like I mentioned the Scottish sentimentalists, having told you about the tripartite story, what the properties are in ordinary natural terms, what they do, they excite an admiration in us, what we express, the admiration, just as they had that three-part story and then stopped. So the pragmatists were very keen that you didn't look at abstractions, you didn't look at things like truth or logic. Peirce has a wonderful saying, we must not start with pure ideas, vagabond thoughts which tramp the public highways with no human habitation, but with men and their conversation. So what you have to do is look at what people are up to or doing.
Yeah.
To that extent, this is a link with the ordinary language movement of Oxford. You don't immediately go for the big abstract terms. So as I put it in one of my books, when Pontius Pilate says, "What is truth?" The right answer, for a deflationist especially, is to say, you tell me what you're interested in. If you're interested in whether this guy's guilty, then the truth consists in him being guilty. If you're interested in showing that, Barabbas is right about everything, then the truth is Barabbas being right about everything.
Yeah.
But you can't say in general what truth is, because I don't know what you're interested in.
Yeah. It's like, what is... Well, I guess you could say truth is... Well, no, it's not even right to say that truth is affirmation.
No.
But it's...
You can affirm falsities.
I agree that the important thing to do is to look at what people are actually doing, right? And I'll run this by you just to round things up here, because I wanted to see what you think of this. Because it's kind of fun to think about, but some people think I'm losing my mind when I start going down this train of thought. Like, let's take the most non-emotive statement we could think of, like, the table exists, right? And then I ask myself, okay, what am I doing when I affirm the table exists? Well, why do I think the table exists? Because I can see it. Okay. Why do I believe that because I can see it, it's there? Well, because I believe that my sense data is accurate. Okay, why do I believe that my sense data is accurate? Well, because if I didn't, I'd be in some kind of, Cartesian skeptical hellhole, right? Okay, why not just do that? And I have to say something like, I just boo,
Yes, boo.
And so if what I'm kind of expressing, at least to some degree, by saying the table exists, is my discontent with the negation of this fundamental premise. Sense data accurate. If I say it's false that my sense data is accurate, and I'm sort of like, no, boo. Like I sort of and when I say that my sense data is accurate, the motivation for saying that, what I'm doing is I'm reacting badly to the opposite. If that's like an expression, like a boo to that, then when I express that the table exists, if that's what I'm fundamentally expressing, then is it not, in some sense, is it not sensible to say that when I say the table exists, I'm to some degree expressing an emotion?
Well, I think you're expressing confidence in your own, the deliverance of your own senses. But of course, we're often not aware of the interconnectedness and therefore the complexity of what we're expressing. I mean, I thought you were going to sort of get not so much onto, a general anti-Cartesian view of your own sense experience, that it can't be just there's a matrix reality. But to point out that to say that the table exists is to have a huge variety of commitments.
Yes.
If you try and occupy that space, you'll fail.
Yeah.
If you try to do all sorts of things, you'd meet resistance from the table. If you put your glass down, it'll be held up. If then. And so, insofar as conditionals have an expressive side to them, they're inference tickets. You've handed yourself a great sheaf of inference tickets. And just by saying the table exists, you're committed, and your expectations spread across, far more than you might have thought.
Yes.
And that I think is fine. It reminds us of the, to use a word I've used quite often, the interconnectedness of things. That is that, philosophy likes to split up into, there's lectures on epistemology, and then there are lectures on metaphysics, and then there are lectures on ethics, and so on. And maybe that's an artifact of the curriculum.
Yeah.
Nothing to do with the way things come together in our minds.
That certainly seems plausible to me. But when I say to people, like, there is some degree to which I think when I say the table exists, what I'm doing is expressing an attitude indirectly, because I'm expressing an attitude towards my sense data, and it might not be your sense data. It's just wherever it happens to bottom out for you, whatever you're doing. So suppose that somehow I broke down my belief that the table existed, and I kept breaking it down, and why, and I got down to the laws of logic themselves. I said, well, because something can't be true and false at the same time. And then you said, why not? I would then still have to say, it just has to be that way. It says, okay, well, just consider for a moment that P is true and false at the same time. What does your brain do? It kind of goes, no. Kind of goes, boo. I'm not. And it doesn't reason it. It's almost pre-rational. It doesn't justify it. It just feels it.
Yes, you can't play the game if you don't see the truth and falsehood.
But if that foundational thing that you are, people call it an intuition. It's just intuitively or maybe self-evidently true. Again, as I mentioned before, I think another good word for that might just be like really strong feeling.
Well, it's possible to expand feeling to all the dispositions of our minds. I think that's...
Yeah. I suppose that's what I'm interested in the legitimacy, not even so much of doing that, but of conceiving of it in that way, of widening our scope of emotive understanding to.
Well, I think it's a good line to follow, because it gets us away from what Wilfrid Sellars called the myth of the given. Sellars thought that one of the great mistakes of modern philosophy, mistake which was basically the split between the analytical movement, Russell and Moore, and the preceding Oxford idealists or Hegel or Kant, was that they thought in atomistic terms. They thought that, the table being there is a datum, it's an item of experience which is given. It's a given to you. Then what was given might only be sense data, but it might be the table if you're more, less of an indirect realist. And Sellar's thought and of course the idealist thought that this was a mistake. A wonderful metaphor Russell mentions is that Bradley, and this is the Oxford idealists of the 19th century, thought that the world was a pot of treacle, whereas Moore and he think that it's a heap of shot. Now, a heap of shot has these sort of atomistic individual shot is, there's nothing much to relate them. They're just, if you pour them out, they're just a heap. Whereas pot of treacle, you can't separate anything out.
Yeah.
And the idea that, the idea of so-called holism came back into philosophy in the middle of the 20th century after it had been exiled by the original analytical philosophers. And with holism comes the kind of view that you've been sympathetic to, that you can't just have one inference. You're going to a piece of datum is going to be a cornucopia of many inferences and many ripples throughout your whole web of belief.
Okay, then one more thing then to round out, which is just one more strategy, a bit of a novel one, let's say, to emotivize propositions or things which are generally not thought to be emotional, like simple propositions like the table exists or whatever. Here's one strategy. We might say, okay, let's suppose that we're like materialists. Let's suppose that all that exists is matter. There's no God. There's no ultimate mind, right? What is a proposition? Well, a proposition is a declarative statement. It says that something is the case, something like that. Okay. So where and in what way and when do propositions exist? Well, for the materialist, propositions only exist when they're being thought or when they're being spoken. Otherwise, propositions don't exist. The things they refer to, like chairs, might exist, but the proposition "the chair is red" only exists when someone's thinking it or speaking it.
Can I just interrupt?
Please.
It seems to me that you're trespassing against Peirce's dictum. But proposition is an abstraction.
Yeah.
Asking what it is already trespassing against the dictum. We must not start with pure ideas, vagabond thoughts that tramp the public highways with no human habitation, but with men and their conversations. Now, how do we use the idea of a proposition in a conversation? Well, we talk about what you said, what you think.
Okay.
Those are propositions.
Okay.
And they're used to locate items of information or misinformation that we want to tell each other about. That is, they have their home in the conversations of people. And I think it's a mistake to ask what they are, as it were. It's obviously, it's like asking, whether the tree falling alone in the forest makes a sound. I think of they are, whether or not anybody's talking, they are what they would be saying if they were talking.
Yeah, but okay, so is it fair to say then that if a proposition exists when it's being spoken or when it's being thought, given that speaking and thinking are both things that people do, they're actions, does that mean I could sort of say that a proposition is an action?
No, I don't think so.
Is it a thing that's thought or a thing that's spoken?
Actions make it salient to talk about them.
Interesting.
You don't want to talk about them if there's no action.
Yeah, because of course the the rounding up of that argument might be that, well, if propositions are in some sense actions or things that people do, actions or things that people do don't have truth value, and therefore propositions wouldn't have truth value, which seems a little bit strange. So I wanted to, I guess, probe how you understand what a proposition is, but I guess just like with the ethical question from earlier, I feel like that's trespassing somewhere that philosophers dare not tread.
Well, I think we've learned the wisdom of not treading there.
Right, I see. Yeah, that's an interesting way of thinking about that problem too. Or whatever the case, it's something that as I said earlier, I think has a surprising connection to what listeners of this show might have heard recently in some of my discussions with physicists about the nature of what science does. In other words, I think if anybody's a little bit dissatisfied with the ethicist sort of saying, well, we just don't do that, we just don't talk about that, we don't go there, you say, well, why not? You could ask the same thing for the scientist who doesn't go there when it comes to the metaphysics of what stuff is actually made of.
Yes, well, there is a wisdom in paring down the number of things that there are to trouble one's pretty head about.
I think that's also
plenty
true.
Enough to trouble one's self about in the world as we have it, not only in the flights of metaphysics.
Yeah, I think it's another great example of why so many people could ridicule philosophy, because you could sit here for 4 hours and discuss what a proposition is, and then go out and not change anything about the way that you actually use them in practice.
Yes, that's right.
But one proposition that
I think philosophers need to shake off that unreal kind of image.
Yeah.
By not dealing with questions which we don't have to deal with.
Yeah. Well, an interesting message and injunction, and I'm genuinely interested to see what people will make of it. Simon Blackburn, thank you so much for taking the time.
Thank you for giving me the time.